Expanding Earth theory emerges from early geological observations that continental margins fit together with remarkable precision when oceanic basins are removed. Pioneering geologists proposing that continental drift results from planetary expansion rather than horizontal plate motion across stable Earth's surface. These early expansion models suggest that continents once covered a smaller Earth completely. Oceanic basins opening through planetary radius increased that stretch continental crust apart while creating new oceanic space between separated continental fragments through gradual planetary growth mechanisms. Continental reconstruction exercises demonstrate that continental shelves fit together like puzzle pieces when mapped onto spheres with smaller radii than modern Earth. Geological fitting exercises revealing optimal continental assembly on Earth models with 60 to 80% of current planetary radius. These reconstruction studies suggest that continental positions during earlier geological periods reflected smaller planetary circumference. Continental separation occurring through planetary expansion rather than drift across constant planetary surface area through horizontal tectonic motion. Beginners' continental drift observations initially lacked convincing mechanisms for continental motion across apparently solid Earth's surface. Continental drift theory requiring extraordinary forces to move continental masses through oceanic crust without clear driving mechanisms. Expanding Earth theory provided alternative explanations for continental motion through planetary growth that separated continents naturally without requiring horizontal continental displacement through resistant oceanic materials. Expansion mechanisms offering more plausible driving forces for continental separation than horizontal drift scenarios. Early expansion theorists including Owen and Carey developed detailed planetary expansion models based on geological observations and continental fitting exercises. Expansion theory attracting significant scientific attention during pre-plate tectonics, geological periods when horizontal drift mechanisms remained unexplained. These historical expansion models established theoretical foundations for planetary growth scenarios while providing alternative explanations for continental distribution patterns that challenged conventional assumptions about planetary size stability. Geological evidence for expansion includes continental margin parallelism, matching geological formations across oceanic basins, and fossil distribution patterns that suggest former continental connectivity across regions now separated by thousands of kilometers of oceanic crust. These geological observations support expansion scenarios where continental separation results from planetary growth rather than horizontal drift. Continental margins preserving evidence of former proximity despite current oceanic separation. Paleomagnetic data analysis reveals continental position changes over geological time that could reflect planetary expansion rather than continental drift. Magnetic pole wandering patterns potentially indicating changing planetary geometry rather than continental motion across stable planetary surfaces. These paleomagnetic studies provide quantitative constraints on expansion scenarios while revealing continental position evolution that could support planetary growth models through magnetic field orientation analysis. Ocean floor age patterns demonstrate systematic oceanic crust age progression from continental margins toward oceanic ridge systems. Age patterns potentially reflecting expansion-driven oceanic crust formation rather than seafloor spreading from fixed ridge locations. These oceanic age distributions could support expansion models where new oceanic crust forms through planetary surface area increase rather than horizontal seafloor spreading mechanisms. Mountain formation processes including folding, faulting, and volcanic activity could result from expansion-induced crustal stress rather than horizontal plate collision. Expansion creating compression and tension patterns that generate observed mountain building and tectonic activity. These mountain formation mechanisms provide expansion explanations for orogenic processes while demonstrating how planetary growth could drive observed geological deformation patterns. Volcanic activity distribution patterns around oceanic ridges and continental margins could reflect expansion-induced crustal fracturing rather than plate boundary activity. volcanic eruptions occurring along expansion-generated fracture systems that provide magma access to surface regions. These volcanic patterns potentially support expansion models where crustal extension creates volcanic activity through expansion-induced fracturing rather than plate tectonic mechanisms. Earthquake distribution and seismic activity patterns could reflect expansion-induced crustal stress rather than plate boundary interactions. Seismic activity occurring along expansion-generated fracture zones and stress concentration areas created by planetary growth processes. These seismic patterns potentially indicate expansion-driven crustal deformation rather than horizontal plate motion through earthquake mechanism analysis. Modern plate tectonic theory replaced expansion models through demonstrating convincing mechanisms for horizontal continental motion, including seafloor spreading, subduction, and mantle convection. Plate tectonics providing comprehensive explanations for geological observations without requiring planetary expansion. However, some expansion advocates argue that plate tectonics cannot fully explain all geological observations, while expansion models provide superior explanations for specific geological phenomena. Some believe expanding Earth theory provides better explanations for continental distribution and geological observations than plate tectonics based on continental fitting exercises and geological evidence analysis, while others maintain that plate tectonics provides more complete and mechanistically sound explanations for geological phenomena despite expansion theory historical significance. The scientific consensus strongly supports plate tectonics, while expansion theory remains minority position with limited contemporary support. Expansion theory revival efforts utilize modern geological data and measurement techniques to test expansion scenarios. Contemporary expansion research investigating whether subtle planetary expansion could operate alongside plate tectonic processes rather than replacing plate tectonics entirely. These modern expansion studies attempt to reconcile expansion concepts with established geological understanding while exploring whether measurable planetary expansion occurs. Historical expansion models established important precedents for questioning assumptions about planetary stability, while demonstrating alternative approaches to geological reasoning that challenged conventional geological thinking. These historical contributions remain significant for geological theory development despite subsequent displacement by plate tectonic theory that provides more comprehensive explanations for geological observations. The irony of expanding Earth theory lies in its prescient recognition that Earth undergoes large-scale changes while proposing incorrect mechanisms for observed geological phenomena. Expansion theory correctly identifying continental motion and geological activity, while incorrectly attributing these phenomena to planetary expansion rather than horizontal plate motion. Early expansion models demonstrating innovative geological thinking that contributed to geological theory development, despite ultimate replacement by more accurate plate tectonic explanations for continental drift and geological activity. Geological evidence for planetary size changes emerges from paleomagnetic data analysis and ancient shoreline measurements that reveal potential Earth radius variations across deep geological time. Sophisticated measurement techniques detecting subtle signatures of planetary expansion or contraction embedded within geological records spanning millions of years. Paleomagnetic field intensity variations preserved in igneous rock suggest possible changes in Earth's magnetic field strength that could reflect alterations in planetary size and core dynamics. Magnetic field intensity potentially correlating with planetary radius through core-mantle electromagnetic relationships. Ancient sea level indicators, including marine fossils, evaporite deposits, and sedimentary formations, preserve information about historical ocean configurations that could reflect changing planetary surface area and oceanic basin volumes. Geological sea level records potentially documenting planetary expansion through increased oceanic basin capacity over geological time. These sea level proxies provide quantitative constraints on planetary size evolution, while revealing oceanic volume changes that could support gradual expansion scenarios through geological sea level analysis. Gravity field measurements from satellite geodesy reveal subtle Earth shape variations and gravitational anomalies that could indicate ongoing planetary expansion or internal mass redistribution. Precision gravity mapping detecting gravitational field changes that might reflect planetary size modifications over decadal to century timescales. These gravitational studies provide contemporary evidence for potential planetary expansion while establishing observational frameworks for detecting subtle planetary size changes through gravitational field monitoring. Crystal thickness variations across continental and oceanic regions preserve information about historical crustal formation processes that could reflect planetary expansion through crustal stretching and thinning during planetary growth episodes. Crustal thickness patterns potentially documenting expansion-induced deformation over geological timescales. These crustal structure studies provide geological evidence for expansion scenarios while revealing crustal evolution patterns that could support planetary growth models through crustal thickness analysis. Radiometric dating of geological formations reveals temporal patterns in rock formation and metamorphism that could reflect cyclical planetary expansion and contraction episodes. Geochronological data potentially documenting periodic planetary size changes through temporal clustering of geological activity during expansion or contraction periods. These temporal patterns provide chronological frameworks for expansion scenarios while revealing geological activity timing that could correlate with planetary size variations. Isotopic ratios in ancient rocks preserve information about historical atmospheric and oceanic conditions that could reflect changing planetary surface area and atmospheric pressure regimes associated with planetary expansion. Isotopic geochemistry potentially documenting expansion effects through atmospheric and oceanic chemistry evolution over geological time. These isotopic studies provide chemical evidence for expansion scenarios while revealing environmental changes that could support planetary growth models. Fossil preservation patterns and sedimentary formation characteristics could reflect changing gravitational field strength and atmospheric pressure associated with planetary expansion. Fossil preservation efficiency and sedimentary structure potentially documenting expansion effects through preservation quality and sedimentary formation processes. These paleontological studies provide biological evidence for expansion scenarios, while revealing environmental conditions that could support planetary size change models. Ancient climate reconstructions from geological and paleontological data reveal climate patterns that could reflect changing planetary surface area and atmospheric dynamics associated with expansion. Paleoclimate data potentially documenting expansion effects through climate system evolution over geological timescales. These climate studies provide environmental evidence for expansion scenarios while revealing atmospheric and oceanic circulation changes that could reflect planetary expansion. Mineral phase transition evidence in deep Earth samples suggests pressure and temperature changes in Earth's interior that could reflect planetary expansion through internal volume changes and phase transformation processes. Mineral physics potentially documenting expansion through mineralogical evidence for internal pressure and temperature evolution. These mineralogical studies provide deep Earth evidence for expansion scenarios while revealing internal conditions that could support planetary growth models. Geological formation thickness patterns and sedimentary accumulation rates preserve information about historical geological processes that could reflect changing planetary surface area and basin subsidence rates associated with expansion. Sedimentary geology potentially documenting expansion through formation thickness and accumulation rate analysis over geological time. These sedimentary studies provide stratigraphic evidence for expansion scenarios while revealing depositional processes that could reflect planetary size changes. Metamorphic grade variations in ancient rock formations could reflect changing pressure and temperature conditions associated with planetary expansion. Metamorphic petrology potentially documenting expansion through pressure-temperature evolution recorded in metamorphic mineral assemblages. These metamorphic studies provide petrological evidence for expansion scenarios while revealing pressure-temperature conditions that could support planetary expansion models. Some believe geological evidence supports subtle planetary expansion based on paleomagnetic data analysis and geological observation patterns, while others maintain that geological observations remain consistent with stable planetary size despite measurement techniques that could potentially detect expansion signatures. The interpretation of geological evidence for planetary expansion continues to be debated as measurement precision improves and geological understanding advances. Volcanic activity timing and distribution patterns could reflect expansion-induced crustal stress and fracturing that creates volcanic eruption opportunities during expansion episodes. Volcanic geology potentially documenting expansion through temporal and spatial volcanic activity patterns that correlate with proposed expansion periods. These volcanic studies provide igneous evidence for expansion scenarios while revealing magmatic processes that could reflect planetary expansion mechanisms. Structural geology analysis of fault systems and deformation patterns could reveal expansion-induced crustal stress and strain that creates characteristic geological structures during planetary growth episodes. Structural analysis potentially documenting expansion through fault orientation and deformation style analysis. These structural studies provide tectonic evidence for expansion scenarios while revealing deformation processes that could support planetary expansion models. The irony of geological expansion evidence lies in its subtlety despite potential magnitude. Planetary expansion potentially proceeding at rates that create dramatic geological consequences over millions of years while remaining below detection thresholds for human observation timescales. Geological evidence preserving expansion signatures in rock formations and geological structures, while expansion rates remain too slow for direct human detection. Geological records documenting planetary changes that exceed human perceptual capabilities while providing evidence for expansion processes that operate beyond human temporal experience through geological timescales that transcend individual human lifespans and historical observation periods. Continental fit without ocean basins reveals remarkable geometric precision when continental margins are reconstructed on smaller Earth models, with oceanic crust removed entirely. Computer-aided continental reconstruction demonstrating near-perfect continental assembly when mapped onto planetary spheres with reduced radii. These reconstruction exercises suggest that continents originally formed continuous land masses covering smaller planetary surfaces. Oceanic basins, representing later additions to planetary surface area through expansion processes that separated continental fragments while creating new oceanic space between formerly adjacent continental masses. Pangea reconstruction problems arise when attempting to fit all continental masses onto current Earth surface area, continental assembly requiring significant overlapping or compression that creates geometric inconsistencies and conventional plate tectonic reconstructions. Expanding Earth models resolved these reconstruction difficulties by proposing that Pangea covered a smaller planetary surface completely. Continental fit achieving geometric precision when oceanic basins are eliminated, and continental masses are assembled on appropriately reduced planetary radii that accommodate complete continental coverage. Continental shelf geometry preservation across oceanic basins demonstrates remarkable structural continuity despite thousands of kilometers of oceanic separation. Continental margin parallelism and geological formation matching suggesting former direct continental connectivity rather than horizontal drift across oceanic barriers. These geometric relationships support expansion scenarios where continental separation results from intervening oceanic basin creation through planetary growth rather than continental drift across pre-existing oceanic surfaces. Geological formation continuity across oceanic basins provides compelling evidence for former continental connectivity. Identical rock formations, mineral deposits, and geological structures appearing on opposite sides of oceanic basins with matching orientations and characteristics. These geological correlations suggest that continental fragments originated as continuous formations before oceanic basin creation separated them through expansion processes rather than horizontal continental displacement across oceanic crust. Paleontological distribution patterns reveal fossil assemblages that suggest continental connectivity during periods when conventional reconstructions predict oceanic separation. Identical species appearing on continental masses now separated by oceanic basins that would have prevented biological migration through oceanic barriers. These biogeographic patterns support expansion models where biological distribution reflects former continental connectivity before oceanic basin formation through planetary expansion separated previously connected continental ecosystems. Mountain range alignment across oceanic basins demonstrates structural continuity that suggests former direct continental connection. Mountain systems exhibiting consistent orientations and geological characteristics despite oceanic separation that appears to interrupt continuous mountain formation processes. These structural alignments support expansion scenarios where mountain systems formed during continental connectivity before oceanic basin creation separated continuous geological structures through planetary growth processes. Sedimentary basin correlation across oceanic regions reveals matching depositional environments and stratigraphic sequences that suggest shared geological history before oceanic separation. Sedimentary formations exhibiting identical characteristics and temporal development patterns despite current oceanic isolation. These sedimentary correlations provide evidence for expansion models where depositional environments developed during continental connectivity before oceanic basin formation through planetary expansion created current continental separation. Volcanic activity patterns and igneous rock distributions could reflect expansion-induced crustal extension that creates systematic volcanic alignment along expansion-generated fracture systems. Volcanic chains potentially marking expansion-related crustal extension zones rather than plate boundary locations. These volcanic patterns provide igneous evidence for expansion processes while revealing magmatic activity distribution that could reflect planetary growth mechanisms rather than conventional plate tectonic processes. Continental margin morphology exhibits characteristics that suggest expansion-related separation rather than horizontal drift. Continental edges displaying structural features consistent with extensional separation rather than transform or collisional margins expected from horizontal plate motion. These morphological characteristics support expansion models where continental margins formed through stretching and separation during planetary growth rather than horizontal continental displacement. Ocean depth distribution patterns reveal systematic relationships between oceanic basin age and water depth that could reflect expansion-driven oceanic basin development. Oceanic depth profiles potentially documenting expansion-related basin formation rather than seafloor spreading from fixed ridge locations. These bathymetric patterns provide oceanographic evidence for expansion scenarios while revealing oceanic basin evolution that could support planetary growth models. Island arc formation and oceanic plateau development could reflect expansion-induced volcanism rather than subduction-related magmatic activity. Oceanic volcanic features potentially forming through expansion-related crustal extension and mantle decompression rather than plate collision processes. These oceanic volcanic features provide marine evidence for expansion mechanisms while revealing igneous activity that could reflect planetary expansion rather than conventional plate tectonic processes. Some believe continental fit evidence provides compelling support for expanding Earth theory based on geometric reconstruction precision and geological correlation patterns, while others maintain that continental fit problems can be resolved through improved plate tectonic reconstruction techniques that account for continental deformation and rotation during drift processes. The interpretation of continental fit evidence continues to be debated as reconstruction techniques improve and geological understanding advances. Crustal age relationships between continental and oceanic regions could reflect expansion processes where oceanic crust formation follows continental separation through planetary growth. Oceanic crust age patterns potentially documenting expansion-driven basin development rather than seafloor spreading mechanisms. These age relationships provide geochronological evidence for expansion scenarios while revealing temporal patterns that could support planetary expansion models. Transformed fault systems and fracture zone development could reflect expansion-induced stress patterns rather than horizontal plate motion. Fault orientations and fracture zone characteristics potentially documenting expansion-related deformation rather than transformed plate boundary activity. These structural features provide tectonic evidence for expansion processes, while revealing deformation patterns that could reflect planetary growth mechanisms. The irony of continental fit precision lies in its demonstration of geometric relationships that appear to require planetary expansion, while conventional geology explains continental distribution through horizontal motion. Continental reconstruction achieving remarkable precision on smaller Earth models, while plate tectonics provides alternative explanations for continental motion that maintain planetary size stability. Geometric evidence suggesting expansion necessity, while established geological theory explains continental distribution without expansion requirements. Continental fit creating compelling expansion evidence, while alternative geological mechanisms account for continental motion through horizontal plate displacement across stable planetary surfaces. Deep Earth mass accumulation operates through continuous cosmic dust accretion, meteorite bombardment, and solar wind particle capture that steadily adds material to planetary mass inventory. Cosmic debris accumulation potentially driving gradual planetary expansion over geological timescales through mass addition rates that exceed atmospheric and surface erosion losses. Interplanetary dust particles continuously rain onto Earth's atmosphere at rates approaching 40,000 tons annually. Cosmic dust accumulation providing steady mass input that could contribute to planetary growth through incremental mass addition over millions of years. Meteorite bombardment contributes additional mass through extraterrestrial rock impacts that deliver substantial material quantities during individual impact events. Large meteorite impacts adding millions of tons of cosmic material, while smaller meteorite impacts provide continuous mass input throughout geological time. These impact delivery mechanisms demonstrate how extraterrestrial material continuously augments planetary mass, while providing potential driving forces for gradual planetary expansion through accumulated mass addition over geological timescales. Solar wind particle capture operates through atmospheric and magnetospheric interactions that trap high-energy particles from solar radiation. Charge particle capture, potentially adding substantial mass to planetary atmosphere and surface over geological time periods through continuous solar particle bombardment. These solar wind interactions provide additional mass input mechanisms while demonstrating how stellar radiation contributes to planetary mass accumulation through particle capture processes that operate continuously throughout planetary evolution. Cosmic ray interactions with atmospheric components create secondary particle cascades that could contribute to atmospheric mass through nuclear reaction products. Cosmic radiation potentially generating additional atmospheric mass through spallation reactions and nuclear transformation processes that add particles to atmospheric inventory. These cosmic ray effects provide nuclear mechanisms for mass addition, while revealing how high-energy radiation contributes to planetary mass accumulation through nuclear processes in atmospheric components. Cometary impact delivery systems provide episodic mass input through volatile-rich impact events that add substantial water, organic compounds, and rocky materials to planetary surface and atmosphere. Cometary bombardment potentially contributing significant mass during heavy bombardment periods while providing continuous background mass input throughout geological time. These cometary delivery mechanisms demonstrate how outer solar system materials contribute to planetary mass accumulation through impact processes that operate over astronomical timescales. Gravitational capture of interstellar material occurs as Earth's gravitational field intercepts cosmic dust and gas during galactic orbital motion. Gravitational capture potentially accumulating interstellar material that adds to planetary mass through gravitational interaction with cosmic material distributions. These gravitational mechanisms provide continuous mass accumulation processes while demonstrating how planetary gravity contributes to mass collection through gravitational interaction with cosmic material flows. Atmospheric erosion rates compared to mass input rates determine net planetary mass change. Atmospheric loss through solar wind sputtering and atmospheric escape potentially balanced or exceeded by cosmic material input, depending on atmospheric retention efficiency and cosmic bombardment rates. These atmospheric balance calculations provide quantitative frameworks for mass accumulation, while revealing net mass change rates that could drive planetary expansion through accumulated mass addition over geological time. Deep mantle mass addition through subduction of oceanic sediments and crustal materials could contribute to interior mass accumulation. Subduction processes potentially adding surface materials to deep Earth regions while contributing to overall planetary mass through tectonic material transport mechanisms. These subduction mass transfer processes provide internal mass redistribution mechanisms while revealing how surface materials contribute to deep Earth mass through tectonic transport processes. Radioactive decay mass-energy relationships demonstrate how nuclear decay processes convert mass to energy while potentially affecting overall planetary mass through Einstein mass-energy equivalence. Radioactive decay potentially reducing planetary mass through energy emission, while cosmic material input provides mass addition that could exceed decay-related mass loss. These nuclear mass-energy calculations provide nuclear physics frameworks for planetary mass evolution, while revealing nuclear contributions to planetary mass change processes. Core formation processes during early planetary development concentrated dense materials toward planetary center, while potentially affecting planetary radius through gravitational contraction and internal mass redistribution. Core formation creating dense central regions that could influence planetary expansion potential through gravitational effects and internal pressure relationships. These core formation mechanisms provide early planetary evolution frameworks for understanding expansion potential through internal mass distribution effects. Volcanic outgassing and magmatic processes transport deep Earth materials to surface regions while potentially contributing to surface mass through mantle-derived material addition. Volcanic activity providing mass transport mechanisms that move internal materials to surface locations while contributing to overall surface mass through magmatic material delivery. These volcanic transport processes provide internal-external mass transfer mechanisms while revealing how deep Earth materials contribute to surface mass through volcanic activity. Some believe cosmic mass accumulation provides sufficient driving force for measurable planetary expansion based on cosmic bombardment rate calculations and mass accumulation estimates, while others suggest that cosmic mass input remains insufficient for significant planetary expansion despite continuous cosmic material delivery. The effectiveness of cosmic mass accumulation for driving planetary expansion continues to be investigated as cosmic bombardment rates are refined and expansion detection capabilities improve. Atmospheric chemistry evolution through cosmic material input could provide chemical signatures of mass accumulation processes. Atmospheric composition changes potentially documenting cosmic material addition through isotopic and chemical analysis of atmospheric components. These atmospheric chemistry studies provide chemical evidence for cosmic mass accumulation, while revealing atmospheric evolution that could reflect cosmic material input over geological time. Geological formation chemistry analysis could reveal cosmic material signatures in sedimentary and igneous formations. Geological chemistry potentially documenting cosmic bombardment through enhanced concentrations of extraterrestrial elements and isotopic signatures that reflect cosmic material input during formation periods. These geological chemistry studies provide terrestrial evidence for cosmic mass accumulation, while revealing chemical signatures that could document cosmic material input. The irony of imperceptible mass accumulation lies in its potential for driving dramatic planetary changes through processes that remain below human detection thresholds. Cosmic material input potentially creating significant planetary expansion over geological time, while operating through individual events and processes that appear insignificant during human observation timescales. Mass accumulation demonstrating how continuous small-scale processes create large-scale planetary evolution through accumulated effects that transcend human perceptual capabilities while operating continuously throughout planetary history at rates that exceed direct human measurement capabilities. Radioactive decay heat generates thermal energy within Earth's interior through uranium, thorium, and potassium isotope decay that produces approximately 20 terawatts of continuous heat output, internal heat generation potentially driving thermal expansion of mineral phases and mantle convection patterns that could contribute to gradual planetary radius increase over geological timescales. Nuclear decay processes operating within Earth's core, mantle and crust, create persistent heat sources that maintain elevated internal temperatures while potentially causing mineral thermal expansion that could accumulate into measurable planetary growth through thermal expansion mechanisms. Thermal expansion coefficients for major Earth materials demonstrate volume increases with temperature elevation. Silicate minerals and metallic phases exhibiting predictable expansion rates that could contribute to planetary radius increase when integrated across entire planetary mass subjected to nuclear heating. Olivine, pyroxene, and feldspar minerals show thermal expansion rates that could generate substantial volume increases when applied to mantle-scale material quantities heated by radioactive decay over millions of years. Thermal expansion potentially creating cumulative planetary growth through mineral volume increase. Mantle convection patterns driven by radioactive heating create upwelling and downwelling flows that transport heat from deep interior regions towards surface, while potentially affecting overall mantle volume through thermal expansion and phase transition processes. Convective heat transport potentially maintains elevated mantle temperatures that sustain thermal expansion, while creating dynamic flow patterns that could facilitate mantle volume increase through thermal expansion enhancement and phase transition effects that favor expanded mineral phases. Core thermal evolution through radioactive decay heating and secular cooling creates complex temperature profiles that affect iron-nickel phase stability and thermal expansion characteristics. Core thermal evolution potentially contributing to planetary expansion through thermal expansion of core materials and phase transitions that favor expanded metallic phases. Core temperatures potentially remain elevated through radioactive heating, while supporting thermal expansion that could contribute to overall planetary radius increase. Through core volume expansion, phase transition effects in deep Earth materials could amplify thermal expansion through pressure-temperature-induced mineral transformations that favor expanded crystal structures. High-pressure mineral phases potentially undergoing volume-increasing phase transitions when heated by radioactive decay. Olivine spinal perovskite transitions and ion phase changes could contribute to planetary expansion when thermal energy shifts phase equilibria toward expanded mineral structures throughout mantle and core regions. Geothermal gradient measurements reveal internal temperature distributions that reflect radioactive heating patterns. Geothermal data providing observational constraints on internal heat generation, while revealing temperature conditions that could drive thermal expansion throughout Earth's interior. Temperature profiles demonstrate substantial internal heating that maintains elevated temperatures capable of driving thermal expansion in deep Earth materials over geological timescales. Seismic velocity measurements detect internal density and elastic property variations that could reflect thermal expansion effects and phase transition contributions to planetary structure evolution. Seismic wave propagation characteristics potentially documenting internal volume changes associated with thermal expansion and phase transitions. Seismic tomography reveals internal structure variations that could reflect ongoing thermal expansion and phase transition processes affecting planetary internal architecture. Volcanic heat flow observations demonstrate surface manifestations of internal thermal energy generation. Volcanic activity providing evidence for substantial internal heat production that could drive thermal expansion while revealing thermal energy transport from deep interior regions. Volcanic heat output potentially reflects internal thermal expansion processes while providing surface evidence for internal heat generation that could contribute to planetary expansion. Laboratory mineral physics experiments under high-pressure, high-temperature conditions reproduce Earth interior conditions while measuring thermal expansion and phase transition effects in Earth materials. Experimental mineral physics providing quantitative data on thermal expansion rates and phase transition volume changes that could affect planetary expansion. These experiments established thermal expansion parameters for Earth materials while revealing volume change mechanisms that could contribute to planetary growth. Numerical modeling of planetary thermal evolution incorporates radioactive decay, heating, and thermal expansion effects to predict planetary radius evolution over geological time. Thermal evolution models potentially predicting measurable planetary expansion through integrated thermal expansion effects operating over millions of years. These computational models provide theoretical frameworks for thermal expansion-driven planetary growth, while establishing quantitative predictions for expansion rates and expansion detection requirements. Isotopic ratios in igneous rocks preserve information about internal temperature evolution and thermal processes. Radiogenic isotope systematics potentially documenting thermal expansion effects through isotopic signatures that reflect internal heating and thermal evolution patterns. These isotopic studies provide geochemical evidence for internal thermal processes while revealing thermal evolution that could support thermal expansion scenarios. Some believe radioactive decay heating provides sufficient thermal energy for measurable planetary expansion based on thermal expansion calculations and internal heat generation estimates, while others suggest that thermal expansion effects remain insufficient for significant planetary growth despite substantial internal heat production. The effectiveness of thermal expansion for driving planetary radius increase continues to be investigated as thermal expansion measurements improve and internal heating estimates are refined. Crustal thermal expansion effects could contribute to surface elevation changes and geological deformation that reflect planetary thermal expansion. Crustal heating, potentially creating surface manifestations of thermal expansion while contributing to overall planetary radius, increase through crustal volume expansion. These crustal thermal effects provide surface evidence for thermal expansion processes while revealing thermal expansion contributions to geological deformation. Deep Earth pressure effects on thermal expansion could modify expansion rates through pressure-dependent thermal expansion coefficients. High-pressure conditions potentially affecting thermal expansion efficiency, while creating pressure-temperature relationships that influence overall planetary thermal expansion. These pressure effects provide additional complexity for thermal expansion calculations, while revealing pressure-temperature interactions that affect planetary thermal expansion mechanisms. The irony of thermal planetary expansion lies in its utilization of nuclear energy for geological change. Radioactive decay providing nuclear heating that drives planetary growth through thermal expansion while operating through nuclear processes that remain invisible to surface observation. Internal nuclear heating creating planetary expansion through thermal mechanisms that accumulate over geological time, while remaining below human detection thresholds despite continuous operation throughout planetary history. Nuclear energy driving geological change through thermal expansion that operates continuously yet imperceptibly while creating potential planetary growth through accumulated thermal expansion effects. Phase transitions in Earth's core create volume changes when iron-nickel alloys undergo pressure-induced crystallographic transformations between different metallic phases. High-pressure mineralogy revealing that iron exhibits multiple phase transitions at pressures and temperatures characteristic of Earth's core conditions. These phase transitions could trigger significant volume expansions when pressure-temperature conditions shift to favor expanded metallic phases. Core phase changes potentially contributing to planetary radius increase through volumetric expansion of core materials during mineralogical transformations. Iron phase diagram complexities demonstrate multiple stable phases including A-iron, E-iron, and liquid phases that exhibit different densities and volume characteristics under extreme pressure and temperature conditions. Phase boundary crossings potentially triggering substantial volume changes when core materials transition between crystallographic structures. The hexagonal, close-packed E-iron phase could expand relative to face-centered cubic phases under specific pressure-temperature conditions. Phase transitions potentially creating core volume increase that contributes to overall planetary expansion. Core mantle boundary conditions provide critical pressure and temperature environments where phase transitions could occur in both metallic core materials and silicate mantle materials. Boundary region phase changes potentially amplifying volume expansion effects through coupled phase transitions in adjacent materials. Temperature fluctuations and pressure variations at core mantle interfaces could trigger synchronized phase transitions that create substantial volume changes affecting both core and lower mantle regions simultaneously. Solidification patterns within Earth's core create ongoing phase transitions as liquid iron crystallizes onto inner core surfaces while releasing latent heat and potentially undergoing volume changes during solid-liquid phase transitions. Inner core growth through progressive solidification could involve volume expansion if solid iron phases occupy greater volumes than liquid phases under core conditions, solidification contributing to planetary expansion through progressive phase transition volume changes. High-pressure experimental studies of iron-nickel alloys reveal phase transition behaviors under Earth core conditions. Laboratory experiments demonstrating volume changes during pressure-induced phase transitions that could scale to planetary dimensions when applied to core-scale material quantities. These experimental results provide quantitative data on phase transition volume changes while establishing physical foundations for core phase transition contributions to planetary expansion. Seismic discontinuities within Earth's interior potentially mark phase transition boundaries where materials undergo density and elastic property changes. Seismic observations revealing internal structure variations that could reflect ongoing phase transitions affecting planetary internal architecture. The 410 km and 660 km seismic discontinuities potentially represent phase transition zones where volume changes could contribute to planetary expansion through progressive phase transition processes. Temperature evolution within Earth's core affects phase stability and phase transition timing. Core cooling and heating cycles potentially triggering periodic phase transitions that create episodic volume changes contributing to planetary expansion. Secular core cooling could shift phase equilibria toward expanded phases, while core heating through radioactive decay or gravitational energy release could trigger alternative phase transitions that affect core volume. Magnetic field generation through core convection potentially reflects phase transition processes and thermal-chemical evolution that affects core volume and planetary magnetic field characteristics. Core phase transitions, potentially influencing magnetic field strength and magnetic field structure through modified convection patterns and electrical conductivity changes. These magnetic field effects provide observational signatures of core phase transitions while revealing core evolution processes that could affect planetary expansion. Pressure-temperature pathway analysis for core evolution reveals potential phase transition sequences that could occur during planetary thermal evolution. Core cooling and heating pathways potentially crossing multiple phase boundaries that trigger sequential volume changes contributing to planetary expansion over geological time. These evolutionary pathways provide temporal frameworks for phase transition-driven expansion while establishing chronological context for expansion processes. Chemical differentiation effects during core formation could establish compositional gradients that affect phase transition behaviors. Core chemical evolution potentially creating conditions that favor volume-expanding phase transitions through compositional effects on phase stability and phase boundary locations. Sulfur, oxygen, and light element incorporation into core materials could modify phase transition characteristics while affecting volume change magnitudes during phase transitions. Elastic property measurements of high-pressure iron phases reveal density and compressibility characteristics that determine volume relationships between different phase structures. Elastic property data providing quantitative foundations for calculating volume changes during phase transitions while establishing physical parameters for planetary expansion calculations. These elastic measurements enable precise volume change estimates for core phase transitions. Some believe core phase transitions provide significant mechanisms for planetary expansion based on high-pressure experimental data and core evolution modeling, while others suggest that phase transition volume changes remain insufficient for measurable planetary growth despite substantial volume changes during individual phase transitions. The effectiveness of core phase transitions for driving planetary expansion continues to be investigated as high-pressure experimental capabilities improve. Inner-outer core boundary evolution through progressive solidification could involve complex phase transition sequences that create cumulative volume changes over geological time. Core solidification potentially contributing to planetary expansion through sustained phase transition processes during core thermal evolution. These solidification processes provide long-term phase transition mechanisms while revealing core evolution contributions to planetary expansion. Core composition uncertainties affect phase transition predictions and volume change calculations. Core light element content and chemical composition potentially modifying phase transition behaviors while affecting volume change magnitudes during core evolution. These compositional effects provide additional complexity for phase transition calculations, while revealing chemical influences on core expansion contributions. The irony of core phase transitions lies in their potential for creating dramatic planetary changes through mineralogical transformations occurring at depths beyond direct observation. Phase transitions, potentially driving planetary expansion through volume changes in materials located thousands of kilometers below surface, while remaining completely inaccessible to direct investigation. Core phase transitions demonstrating how deep Earth processes could affect planetary dimensions through mechanisms that operate beyond human observational access, despite potentially creating measurable surface effects through accumulated volume changes that propagate from core regions to planetary surface through progressive phase transition contributions to planetary expansion. Gravitational constant variations over cosmic time emerge from theoretical physics investigations into fundamental constant evolution. Some cosmological models and quantum gravity theories suggesting that Newton's gravitational constant g may undergo slow temporal changes that affect gravitational binding strength throughout universe evolution. These gravitational constant variations could modify planetary gravitational self-energy and gravitational binding, potentially driving planetary expansion or contraction through altered gravitational field strength that changes equilibrium planetary radius when gravitational binding weakens or strengthens over geological timescales. Variable physical constant scenarios arise from cosmological theories including string theory, extra-dimensional physics, and scalar field cosmology that predict fundamental constant evolution during cosmic expansion. Physical constant variation potentially affecting gravitational physics and planetary structure through modified force relationships. Gravitational constant changes of parts per billion annually could accumulate over geological time to create measurable effects on planetary gravitational binding while remaining below current detection thresholds for contemporary physics measurements. Planetary equilibrium radius relationships depend on gravitational self-energy balance between gravitational attraction and internal pressure gradients. Planetary radius adjusting to maintain hydrostatic equilibrium when gravitational constant changes modify gravitational binding strength. Decreasing gravitational constant values could reduce gravitational binding sufficiently to allow planetary expansion through reduced gravitational attraction. Planetary radius increasing to maintain pressure equilibrium when gravitational forces weaken over cosmic time. Solar system dynamics effects from gravitational constant variation include orbital radius changes and planetary motion modifications that could provide observational signatures of fundamental constant evolution. Planetary orbital characteristics potentially preserving information about gravitational constant history through orbital evolution analysis. Lunar recession rates and planetary orbital expansion could reflect gravitational constant weakening, while providing observational tests for fundamental constant variation through precision orbital measurement and gravitational dynamics analysis. Stellar evolution modifications through gravitational constant changes affect stellar structure and stellar burning rates. Stellar physics potentially providing independent evidence for gravitational constant variation through stellar evolution timing and stellar characteristic modifications. Main sequence lifetime changes and stellar structure evolution could reflect gravitational constant variation, while providing astrophysical tests for fundamental constant evolution through stellar physics observations and stellar evolution modeling. Laboratory tests for gravitational constant variation utilize precision gravitational measurements and atomic clock comparisons to detect fundamental constant changes. Experimental physics potentially achieving sensitivity sufficient for detecting gravitational constant variation through ultra-precision measurement techniques. Gravitational constant measurements over decades could reveal temporal trends, while atomic clock networks could detect fundamental constant variation through precision timing and frequency measurement comparisons. Geological evidence for gravitational constant variation could include gravity signatures preserved in sedimentary formations, and biological fossils that reflect different gravitational field strength during earlier geological periods. Geological records potentially documenting gravitational constant history through sedimentation patterns and biological adaptation evidence. Ancient atmospheric pressure indicators and fossil preservation characteristics could reflect different gravitational conditions while providing geological tests for gravitational constant variation. Big Bang nucleosynthesis constraints on fundamental constant variation established limits on gravitational constant changes during early cosmic epochs. Primordial element abundance patterns requiring specific fundamental constant values for successful light element production during Big Bang nucleosynthesis. These cosmological constraints limit gravitational constant variation rates while providing observational frameworks for fundamental constant evolution through primordial nucleosynthesis abundance analysis. Modified gravity theories, including scalar tensor gravity and FR gravity, predict gravitational constant variation through additional gravitational degrees of freedom. Alternative gravity theories, potentially explaining gravitational constant evolution through extended gravitational physics that transcends general relativity limitations. These modified gravity frameworks provide theoretical foundations for gravitational constant variation while establishing alternative gravitational physics that could drive planetary expansion through fundamental constant evolution. Quantum gravity effects on fundamental constants arise from quantum gravitational corrections to classical gravitational physics. Quantum gravity potentially predicting fundamental constant evolution through quantum mechanical modifications to gravitational field equations. Loop quantum gravity and string theory framework suggest possible mechanisms for fundamental constant variation while providing quantum gravitational foundations for gravitational constant evolution over cosmic timescales. Cosmological observations, including supernovae distances and cosmic microwave background characteristics, provide observational constraints on fundamental constant variation over cosmic history. Cosmological data potentially revealing fundamental constant evolution through modified cosmological expansion and structure formation. These observational constraints establish limits on gravitational constant variation while providing empirical frameworks for fundamental constant evolution through cosmological observation and analysis. Some believe gravitational constant variation provides plausible mechanisms for planetary expansion based on theoretical physics predictions and cosmological observations, while others suggest that gravitational constant remains sufficiently stable to prevent significant planetary expansion, despite theoretical possibilities for fundamental constant evolution. The magnitude and rate of gravitational constant variation continue to be investigated as theoretical physics advances and observational precision improves. Atomic physics effects from fundamental constant variation include modified atomic energy levels and nuclear physics changes that could provide sensitive tests for fundamental constant evolution. Atomic and nuclear physics potentially achieving ultimate sensitivity for detecting fundamental constant variation through precision spectroscopy and nuclear decay measurements. These atomic physics tests provide laboratory frameworks for fundamental constant variation detection, while establishing high-precision measurement techniques for constant variation investigation. Planetary magnetic field effects from gravitational constant variation could modify magnetic field generation through altered planetary rotation and core dynamics. Planetary magnetic fields potentially providing additional observational signatures of gravitational constant variation through magnetic field strength and magnetic field structure evolution. These magnetic field studies provide geophysical tests for gravitational constant variation while revealing planetary physics effects of fundamental constant evolution. The irony of gravitational constant variation lies in its potential for creating planetary expansion through weakening of the very force that holds planets together. Gravitational constant reduction potentially driving planetary expansion by reducing gravitational binding while gravity simultaneously provides the fundamental force that creates planetary structure. Fundamental constant variation creating planetary growth through weakening fundamental forces while demonstrating how cosmic evolution affects planetary physics through mechanisms that transcend local planetary processes. Gravitational constant variation potentially operating at rates too slow for direct detection while accumulating over geological time to create measurable planetary expansion through cosmic evolution effects on fundamental physics. Measurement precision and detection limits create fundamental challenges for detecting gradual planetary expansion that operates at geological rates potentially below current observational thresholds. Modern satellite geodesy and laser ranging achieving millimeter precision for planetary radius measurements, while potential expansion rates of centimeters per million years remain below detection sensitivity for human observation timescales. These measurement limitations demonstrate how extremely slow geological processes could operate continuously, while remaining invisible to contemporary measurement techniques that achieve remarkable precision over short timescales, yet lack temporal coverage for detecting imperceptible long-term changes. Global Positioning System precision enables centimeter-level accuracy for surface position measurements across planetary scales. GPS networks providing continuous monitoring capabilities that could theoretically detect planetary expansion if expansion rates exceed measurement precision over observation periods. However, expansion rates predicted by expansion theories often fall below GPS detection thresholds when integrated over typical satellite mission durations of decades. Expansion detection requiring measurement precision maintenance over centuries or millennia for conclusive expansion confirmation. Very long baseline interferometry achieves sub-millimeter precision for intercontinental distance measurements through radio telescope networks that monitor baseline length changes with extraordinary accuracy. VLBI providing ultimate precision for detecting planetary size changes through baseline expansion measurements. These interferometric techniques establish current technological limits for expansion detection, while demonstrating measurement capabilities that approach theoretical requirements for expansion detection over century-scale observation periods. Satellite laser ranging utilizes laser pulse timing to measure distances between ground stations and orbital satellites with millimeter precision. Laser ranging providing independent measurements of planetary radius changes through satellite orbital analysis and ground station distance monitoring. SLR measurements accumulate over decades while providing increasing sensitivity for detecting systematic planetary expansion through improved measurement statistics and extended observation baselines. Tidal gauge networks monitor sea level variations that could reflect planetary expansion through changing oceanic basin volumes. Sea level measurements potentially providing indirect evidence for expansion through oceanic volume changes associated with planetary radius increase. However, tidal gauge measurements suffer from local geological effects, ocean dynamics, and climate variations that complicate expansion signal detection through sea level analysis. Gravimeter measurements detect gravitational field variations that could reflect planetary mass redistribution or planetary size changes. Precision gravity monitoring potentially revealing expansion signatures through systematic gravitational field modifications associated with planetary growth. However, gravitational signals from expansion remain small compared to measurement noise and local gravitational effects from geological processes and hydrological variations. Seismic wave travel time analysis provides information about internal Earth structure that could reveal expansion through systematic velocity changes and internal density modifications. Seismic tomography potentially detecting expansion effects through modified wave propagation characteristics over time. However, seismic velocity variations from expansion compete with natural seismic velocity variations from mantle convection and thermal evolution. Atomic clock networks achieve ultimate timing precision that could detect fundamental physics changes associated with expansion, including gravitational redshift modifications and fundamental constant variations. Atomic timing providing potential expansion detection through precision physics measurements. These atomic clock measurements establish technological frontiers for expansion detection, while providing sensitivity to fundamental physics effects that could accompany planetary expansion. Error analysis for expansion detection reveals measurement uncertainties and systematic effects that could mask expansion signals. Measurement error propagation potentially preventing expansion detection even with ideal measurement precision due to systematic measurement biases and environmental effects. These error analyses establish requirements for expansion detection while revealing measurement challenges that limit expansion detection capabilities. Statistical analysis requirements for expansion detection demand extended observation periods and multiple independent measurement techniques to achieve statistical significance for expansion confirmation. Expansion signal detection requiring measurement statistics that exceed background measurement variations. These statistical requirements demonstrate temporal constraints on expansion detection while revealing observation duration requirements for conclusive expansion confirmation. Technological improvement prospects for expansion detection include next-generation satellite systems and improved measurement techniques that could achieve enhanced sensitivity for detecting subtle planetary expansion. Future measurement systems, potentially achieving precision sufficient for expansion detection through technological advancement. These technological prospects provide frameworks for future expansion detection, while establishing development pathways for improved expansion measurement capabilities. Some believe current measurement precision approaches sensitivity required for expansion detection based on measurement capability analysis and expansion rate predictions, while others suggest that expansion detection requires measurement precision improvements beyond current technological capabilities, despite remarkable contemporary measurement accuracy. The adequacy of current measurement precision for expansion detection continues to be evaluated as measurement techniques improve and expansion theories are refined. Long-term monitoring program requirements for expansion detection include sustained measurement campaigns over decades to centuries with maintained measurement precision and measurement technique consistency. Expansion detection demanding unprecedented measurement program duration and measurement system stability. These monitoring requirements establish institutional frameworks for expansion detection while revealing organizational challenges for sustained expansion measurement programs. Calibration stability requirements for expansion detection demand a measurement system calibration maintenance over extended periods. Measurement calibration drift, potentially masking expansion signals through systematic measurement variations that mimic or obscure genuine expansion effects. These calibration requirements provide technical frameworks for expansion detection, while establishing measurement system requirements for reliable expansion monitoring. The irony of measurement precision limitations lies in achievement of extraordinary measurement accuracy that remains insufficient for detecting processes that could create dramatic planetary changes over geological time. Measurement technology achieving millimeter precision for planetary measurements, while potential expansion processes operate at rates that require millimeter precision sustained over millions of years for detection. Technological measurement capability approaching theoretical limits, while expansion detection requires temporal measurement persistence that exceeds technological system lifetimes. Measurement precision advancing toward ultimate physical limits, while expansion detection requires measurement program duration that transcends human technological development timescales and institutional stability periods. Plate tectonics, alternative explanations through Earth expansion models attempt to account for seafloor spreading, mountain formation, and volcanic activity by proposing that these phenomena result from planetary growth rather than horizontal plate motion mechanisms across stable planetary surfaces. Expansion theory suggests that oceanic ridges represent sites of crustal extension during planetary growth where new crustal material forms through decompression, melting, and crustal stretching. Ridge volcanism reflecting expansion-induced crustal fracturing rather than seafloor spreading from fixed ridge locations through horizontal plate divergence. Seafloor spreading reinterpretation through expansion models proposes that symmetric magnetic stripe patterns on oceanic floors result from expansion-induced crustal formation rather than horizontal spreading from ridge axes. Magnetic reversal recording occurring during crustal formation through expansion processes, while oceanic age patterns reflect expansion timing rather than spreading rates from ridge systems. These expansion explanations attempt to account for oceanic crust age distribution and magnetic stripe symmetry. through planetary growth mechanisms that create new oceanic crust through expansion rather than horizontal divergence. Mountain formation mechanisms in expansion models suggest that compressive mountain building results from crustal buckling and compression during expansion episodes. Expansion creating crustal stress patterns that generate folding and thrusting through expansion-induced deformation rather than horizontal plate collision. Expansion advocates propose that mountain ranges formed through crustal compression during expansion acceleration periods, while crustal extension during expansion deceleration creates normal faulting and rift valley formation. Subduction zone reinterpretation through expansion theory proposes that apparent subduction represents crustal consumption through expansion-related processes rather than horizontal plate convergence. Oceanic trenches, potentially representing crustal adjustment zones during expansion rather than sites of oceanic plate subduction beneath continental plates. Expansion models attempt to explain volcanic arc formation and deep earthquake patterns through expansion-induced crustal processes rather than subduction-driven magmatism and deformation. Transform fault systems in expansion models represent adjustment zones during non-uniform expansion rather than horizontal plate motion accommodation. Transform faulting potentially reflecting differential expansion rates between adjacent crustal regions rather than horizontal shear motion between moving plates. Expansion advocates suggest that transform fault orientations and displacement patterns reflect expansion stress fields rather than horizontal plate motion vectors. Volcanic activity distribution patterns could reflect expansion-induced crustal fracturing and decompression melting rather than plate boundary volcanism. Volcanic chains potentially marking expansion-related fracture systems where crustal extension creates magma access to surface regions. Expansion models propose that mid-ocean ridge volcanism, island arc volcanism, and continental volcanism all reflect expansion-induced crustal processes rather than distinct plate tectonic volcanic environments. Earthquake distribution and seismic activity patterns in expansion models reflect crustal stress and adjustment during planetary growth rather than plate boundary interactions. Earthquake mechanisms potentially documenting expansion-induced deformation rather than horizontal plate motion and plate collision processes. Expansion advocates suggest that earthquake focal mechanisms and seismic energy release patterns reflect expansion stress fields rather than plate tectonic stress systems. Continental drift mechanisms through expansion eliminate requirements for horizontal continental motion across oceanic barriers. Expansion providing natural continental separation mechanisms through intervening oceanic basin creation rather than requiring continental displacement across pre-existing oceanic crust. Expansion models suggest that continental motion reflects passive continental separation during oceanic basin formation rather than active continental drift through oceanic resistance. Paleomagnetic polar wandering interpretation through expansion models proposes that apparent polar wandering reflects planetary geometry changes during expansion rather than continental drift relative to stable magnetic pole positions. Polar wandering patterns potentially documenting expansion-related continental position changes rather than horizontal continental motion. Expansion advocates suggest that paleomagnetic data support expansion scenarios through apparent polar wandering that reflects planetary geometry evolution. Geological timescale relationships in expansion models suggest that major geological events and extinction episodes correlate with expansion episodes rather than plate tectonic reorganization. Geological event timing potentially reflecting expansion-induced environmental changes rather than plate motion effects on climate and biological evolution. Expansion advocates propose that geological periodicity reflects expansion cycles rather than plate tectonic cycles. Heat flow patterns and geothermal energy distribution could reflect expansion-induced thermal processes rather than plate tectonic heat transport. Heat flow variations potentially documenting expansion-related thermal evolution rather than plate motion effects on thermal structure. Expansion models suggest that oceanic heat flow patterns reflect expansion thermal processes rather than seafloor spreading thermal characteristics. Some believe expansion models provide superior explanations for geological observations compared to plate tectonics based on continental fit precision and geological correlation patterns, while others maintain that plate tectonics provides more comprehensive and mechanistically sound explanations for geological phenomena despite expansion theory, alternative interpretations. The scientific consensus strongly supports plate tectonics, while expansion alternatives remain minority positions with limited contemporary acceptance. Crustal thickness variations and crustal structure patterns in expansion models reflect expansion-induced crustal evolution, rather than plate tectonic crustal formation and modification. Crustal architecture potentially documenting expansion processes rather than horizontal plate motion effects on crustal structure. Expansion advocates suggest that crustal thickness patterns support expansion scenarios through crustal structure that reflects planetary growth processes. Mantle convection relationships to surface geology and expansion models propose that convection patterns reflect expansion-induced internal circulation rather than driving forces for plate motion. Mantle dynamics potentially responding to expansion rather than creating plate tectonic surface motion. Expansion advocates suggest that mantle convection accommodates expansion rather than driving horizontal plate motion through convective circulation patterns. The irony of plate tectonic alternative explanations lies in their attempt to account for well-established geological phenomena through mechanisms that require planetary expansion, while geological observations that originally supported expansion theory are now explained more comprehensively through plate tectonics. Expansion models, providing alternative interpretations for geological observations, while plate tectonics offers more complete explanations for geological phenomena through horizontal plate motion mechanisms that operate without requiring planetary size changes. Expansion alternatives demonstrating scientific creativity while competing with established geological theory that explains geological observations more thoroughly through conventional plate tectonic mechanisms. Fossil distribution and biogeographic patterns preserve ancient life distribution across continental masses that suggest different Earth configurations during earlier geological periods. Paleontological evidence revealing species distributions that appear to require continental connectivity or different oceanic basin configurations that could reflect smaller planetary radius during biological evolution. Ancient life forms including Glossopteris flora, Mesosaurus reptiles, and Lystrosaurus mammals appear on continental masses now separated by oceanic barriers that would have prevented biological migration without land bridge connections or former continental proximity. Glossopteris fossil distribution spans southern continents including South America, Africa, Antarctica, Australia, and India, with identical species appearing across regions now separated by thousands of kilometers of oceanic water. Botanical fossil evidence suggesting former continental connectivity that enabled plant species dispersal across regions now isolated by oceanic barriers. Glossopteris seed fern distribution patterns appearing consistent with oceanic separation during Permian periods when these plants flourished. Fossil evidence potentially supporting continental configurations that differ from current planetary geography. Mesosaurus fossil occurrence in both South America and Africa demonstrates freshwater reptile distribution across Atlantic Ocean regions. Paleontological evidence revealing identical freshwater species on continental masses now separated by oceanic barriers that would prevent freshwater reptile migration. Mesosaurus distribution patterns suggest former land connections or smaller oceanic separation that permitted freshwater species dispersal between South American and African continental regions during Permian geological periods. Lystrosaurus fossil distribution across Antarctica, South Africa and India reveals mammal-like reptile species that appear on continental masses now separated by oceanic and geographic barriers. Lystrosaurus paleontology demonstrating land animal distribution patterns that require continental connections during Triassic periods when these animals lived. Lystrosaurus distribution appears inconsistent with current continental separation, while supporting continental configurations that permitted land animal migration across regions now isolated by oceanic barriers. Paleoclimatic evidence from fossil assemblages reveals climate patterns that suggest different latitudinal positions for continental masses during earlier geological periods. Ancient climate reconstruction indicating tropical conditions in regions now located at high latitudes, while glacial conditions occurred in regions now situated at tropical latitudes. These paleoclimatic patterns could reflect different continental positions on smaller planetary surfaces, where continental masses achieved different latitudinal distributions that created observed ancient climate patterns. Coal deposit distribution across multiple continents reveals similar depositional environments and plant assemblages that suggest coordinated tropical conditions across regions now located at different latitudes. Coal formation requiring tropical swamp conditions that appear to have occurred simultaneously across continental masses, now separated by oceanic barriers and latitudinal differences. Coal deposit correlation across continents suggests former tropical belt configurations that could reflect different planetary geometry during coal formation periods. Marine fossil distribution patterns reveal oceanic species that appear in geological formations now located on continental interiors. Marine fossil occurrence in continental regions suggesting former oceanic coverage or different oceanic basin configurations during marine fossil deposition periods. Marine fossil evidence could support different planetary surface configurations, where oceanic coverage and continental positions differed substantially from current geographical arrangements. Glacial deposit correlation across southern continents reveals similar glaciation patterns and glacial formation characteristics that suggest coordinated ice age conditions across regions now located at different latitudes. Glacial evidence requiring ice sheet formation across continental masses now situated at different climatic zones. Glacial deposit patterns could reflect former continental clustering at polar latitudes on smaller planetary surfaces, where continental masses achieved polar positions that created observed glaciation patterns. Endemic species evolution patterns on isolated continents reveal biological evolution that reflects continental isolation timing. Species endemism, potentially documenting continental separation chronology through biological evolution that occurred after continental connectivity ended. Endemic species distribution could provide temporal constraints on continental separation while revealing biological consequences of changing continental configurations through evolutionary isolation. Biogeographic province boundaries correspond to oceanic barriers and continental boundaries that reflect current geographical configurations. Biological province patterns potentially preserving information about former geographical configurations that influence biological evolution and species distribution. Biogeographic boundary evolution could document changing planetary geography through biological response to continental separation and oceanic basin formation. Migration route paleontology reveals animal migration patterns that suggest former land connections, or different oceanic configurations that permitted biological migration between regions now separated by oceanic barriers. Animal migration evidence potentially supporting former continental connectivity that enabled intercontinental biological exchange. Migration paleontology could document former planetary configurations through biological migration evidence that requires land connections between currently separated regions. Some believe fossil distribution patterns provide compelling evidence for former continental connectivity that supports expansion scenarios based on paleontological evidence for biological exchange between currently separated continental masses. While others maintain that fossil distribution patterns can be explained through conventional plate tectonic continental drift that created former continental connectivity without requiring planetary expansion. The interpretation of paleontological evidence for continental connectivity continues to be debated as paleontological understanding advances and continental reconstruction techniques improve. Extinction event correlation across continents reveals synchronized biological extinction patterns that could reflect coordinated environmental changes associated with planetary expansion episodes. Mass extinction timing potentially correlating with expansion-induced environmental modifications that affected global biological systems. Extinction event analysis could provide temporal frameworks for expansion episodes while revealing biological consequences of planetary expansion through environmental change effects on biological evolution. Species radiation patterns following continental separation reveal biological diversification that occurred after continental connectivity ended. Adaptive radiation potentially documenting continental separation timing through biological evolution that occurred in response to geographical isolation. Species radiation analysis could provide temporal constraints on continental separation, while revealing biological consequences of changing planetary configurations through evolutionary diversification. The irony of biogeographic expansion evidence lies in its preservation of biological signatures for continental connectivity that could support expansion scenarios, while contemporary biology demonstrates species distribution that reflects current planetary geography. Fossil evidence suggesting former continental configurations that differ from current geography, while modern biogeography reflects current geographical barriers and continental isolation. Paleontological evidence potentially supporting planetary expansion through biological distribution patterns, while contemporary biology operates within current planetary geographical constraints that appear stable over human observation timescales despite potential geological expansion processes. Ocean basin age and expansion rates reveal systematic oceanic crust age patterns that could reflect Earth expansion rather than seafloor spreading. Magnetic stripe analysis and radiometric dating demonstrating that oceanic crust exhibits age progression from continental margins toward oceanic ridge systems, with maximum oceanic ages approaching 200 million years. These oceanic age distributions could support expansion models where new oceanic crust forms through planetary surface area increase rather than horizontal seafloor spreading from fixed ridge locations, expansion rates potentially matching oceanic crust formation rates through planetary growth mechanisms. Magnetic reversal recording in oceanic crust creates symmetric stripe patterns that expansion advocates interpret as evidence for expansion-driven crustal formation rather than seafloor spreading. Magnetic polarity transitions preserving temporal information about crustal formation timing during expansion episodes. Expansion models propose that magnetic stripe symmetry reflects bidirectional crustal formation during expansion rather than spreading from ridge axis. Magnetic reversal chronology potentially documenting expansion rates through magnetic stripe analysis and paleomagnetic temporal correlation. Oceanic crust thickness measurements reveal systematic thickness variations that could reflect expansion-induced crustal formation processes rather than seafloor spreading mechanisms. Crustal thickness patterns potentially documenting expansion-related crustal production rather than ridge-spreading crustal generation. Expansion advocates suggest that oceanic crustal architecture reflects expansion processes through crustal thickness distributions that correlate with expansion-driven crustal formation rather than horizontal spreading from ridge systems. Ridge axis geometry and ridge system evolution could reflect expansion-induced crustal fracturing rather than seafloor spreading plate boundaries. Ridge morphology potentially indicating expansion-related crustal extension zones rather than divergent plate boundaries where horizontal spreading occurs. Expansion models propose that ridge systems mark expansion-induced crustal fracture zones, where planetary growth creates crustal extension and decompression, melting rather than representing spreading centers for horizontal plate divergence. Oceanic basin volume calculations reveal substantial water volume requirements for current oceanic basins that could reflect expansion-driven basin formation. Oceanic volume estimates potentially supporting expansion scenarios where oceanic basins represent additional planetary surface area created through expansion rather than pre-existing features filled through volcanic outgassing and cometary water delivery. Expansion advocates suggest that oceanic basin volumes exceed water production capabilities without expansion-driven basin creation. Transform fault offset measurements and transform fault evolution patterns could reflect expansion-induced differential crustal motion rather than horizontal plate motion accommodation. Transform fault displacement potentially documenting expansion-related crustal adjustment rather than strike-slip motion between horizontally moving plates. Expansion models propose that transform fault systems accommodate non-uniform expansion rates between adjacent crustal regions, rather than providing mechanical connections between spreading ridge segments. volcanic production rates at oceanic ridges reveal magma generation rates that could reflect expansion-induced decompression, melting rather than seafloor spreading volcanism. Ridge volcanic output potentially documenting expansion-related magma production through crustal extension and mantle decompression, rather than ridge-spreading volcanic processes. Expansion advocates suggest that ridge volcanism reflects expansion-induced crustal fracturing that creates magma access to surface regions, rather than spreading-related volcanic activity. Oceanic heat flow patterns demonstrate thermal characteristics that could reflect expansion-induced thermal processes, rather than seafloor spreading thermal evolution. Oceanic thermal structure potentially documenting expansion-related heat transport rather than spreading ridge thermal effects on oceanic crust temperature evolution. Expansion models propose that oceanic heat flow reflects expansion thermal processes rather than thermal cooling patterns associated with horizontal seafloor spreading from ridge sources. Sediment accumulation patterns on oceanic floors reveal depositional characteristics that could reflect expansion-induced oceanic basin evolution rather than seafloor spreading sedimentary processes. Oceanic sedimentary sequences potentially documenting expansion-related basin development rather than sediment accumulation on spreading oceanic crust. Expansion advocates suggest that oceanic sedimentary patterns reflect expansion-driven basin formation rather than sedimentation on horizontally spreading oceanic floors. Oceanic plateau formation and oceanic volcanic features could reflect expansion-induced volcanism rather than hotspot volcanic activity. Oceanic volcanic provinces potentially indicating expansion-related magmatic processes rather than mantle plume volcanism or spreading ridge volcanic activity. Expansion models propose that oceanic volcanic features reflect expansion-induced crustal extension and volcanic activity, rather than conventional hotspot or ridge volcanic mechanisms. Gravity anomaly patterns over oceanic basins reveal density structure variations that could reflect expansion-induced crustal architecture, rather than seafloor spreading density characteristics. Oceanic gravity signatures potentially documenting expansion-related crustal structure rather than gravity patterns associated with horizontal seafloor spreading processes. Expansion advocates suggest that oceanic gravity anomalies reflect expansion crustal formation rather than spreading ridge gravity characteristics. Some believe oceanic age patterns and expansion rate calculations provide compelling evidence for Earth expansion, based on oceanic crust formation analysis and magnetic stripe interpretation, while others maintain that oceanic age patterns demonstrate seafloor spreading processes that operate without requiring planetary expansion, despite expansion theory alternative interpretations. The scientific consensus supports seafloor spreading explanations for oceanic crust age patterns, while expansion alternatives remain minority positions. Oceanic crustal composition and geochemical characteristics could reflect expansion-induced magma generation rather than seafloor spreading magmatic processes. Oceanic basalt geochemistry potentially documenting expansion-related magma sources rather than ridge-spreading magmatic evolution. Expansion models propose that oceanic crustal geochemistry reflects expansion-induced mantle melting, rather than seafloor spreading magma generation through ridge volcanic processes. Deep ocean drilling results and oceanic crust sampling reveal crustal characteristics that could support expansion scenarios through crustal formation evidence. Oceanic drilling potentially providing direct evidence for expansion-induced crustal formation, rather than seafloor spreading crustal generation through drilling, sample analysis, and oceanic crustal architecture investigation. These drilling studies provide empirical constraints on oceanic crustal formation, while revealing crustal characteristics that could distinguish expansion from spreading mechanisms. The irony of oceanic expansion evidence lies in its utilization of oceanic features that were originally interpreted as evidence against continental drift to support planetary expansion. Oceanic basin characteristics initially challenging continental drift theory, while potentially supporting expansion theory through oceanic age patterns and oceanic crustal formation mechanisms. Oceanic evidence creating challenges for early continental drift models, while potentially providing support for expansion alternatives that attempt to explain oceanic features through planetary growth rather than horizontal plate motion. Oceanic basins representing both obstacles to continental drift acceptance and potential evidence for expansion processes through oceanic crustal formation patterns. Atmospheric pressure in ancient climates reveal Paleo's environmental conditions that could reflect different Earth surface area, and gravitational field strength during earlier geological periods. Ancient atmosphere reconstruction suggesting atmospheric pressure variations that might indicate changing planetary surface area through expansion, modified atmospheric distribution over larger planetary surfaces. Atmospheric pressure reconstruction through geological and paleontological proxies potentially documents planetary expansion through atmospheric pressure reduction associated with atmospheric distribution over increased planetary surface area during expansion episodes. Ancient air bubble analysis in amber and ice core samples preserves direct atmospheric samples that reveal atmospheric composition and pressure characteristics during earlier geological periods. Trapped atmospheric samples potentially providing evidence for different atmospheric pressure regimes that could reflect changing planetary surface area through expansion-induced atmospheric pressure modifications. These atmospheric samples establish empirical constraints on ancient atmospheric conditions, while revealing atmospheric characteristics that could support expansion scenarios through pressure and composition analysis. Paleontological respiratory evidence from ancient organism physiology and respiratory system characteristics suggests atmospheric conditions that could reflect different gravitational field strength and atmospheric pressure during biological evolution. Ancient organism respiratory adaptations, potentially documenting atmospheric pressure variations that reflect changing planetary conditions through expansion, modified atmospheric characteristics. Respiratory system evolution could provide biological evidence for atmospheric pressure changes associated with planetary expansion through physiological adaptation analysis. Geological formation characteristics, including sedimentary structure and depositional environment indicators, reveal atmospheric and oceanic conditions that could reflect changing planetary surface area. Sedimentary formation analysis, potentially documenting expansion effects through depositional environment evolution that reflects changing atmospheric and oceanic conditions during expansion episodes. Sedimentary geology could provide geological evidence for expansion through formation characteristics that reflect modified environmental conditions. Volcanic outgassing patterns and volcanic emission compositions preserve information about atmospheric evolution that could reflect changing planetary surface area and atmospheric pressure modification through expansion-induced atmospheric redistribution. Volcanic atmospheric contribution potentially documenting expansion effects through atmospheric composition evolution that reflects changing planetary conditions. Volcanic outgassing analysis could reveal atmospheric evolution patterns that support expansion scenarios through atmospheric chemistry and pressure evolution. Ocean chemistry evolution and marine geochemistry patterns reveal oceanic condition changes that could reflect changing oceanic basin volume and atmospheric oceanic interaction modification through expansion-induced oceanic basin enlargement. Oceanic chemistry evolution potentially documenting expansion through marine chemistry patterns that reflect changing oceanic conditions during expansion episodes. Marine geochemistry could provide oceanic evidence for expansion through chemical evolution that reflects oceanic basin modification. Climate model reconstruction for ancient periods reveal climate patterns that could reflect different planetary surface area and atmospheric circulation modification through expansion-induced climate system changes. Paleoclimate modeling potentially documenting expansion effects through climate evolution that reflects changing planetary surface characteristics during expansion episodes. Climate reconstruction could provide atmospheric evidence for expansion through climate pattern analysis that reflects planetary surface area changes. Atmospheric escape rates and atmospheric retention efficiency calculations suggest atmospheric loss mechanisms that could interact with expansion processes. Atmospheric evolution potentially reflecting combined effects of atmospheric escape and expansion, induced atmospheric redistribution over changing planetary surface area. Atmospheric escape analysis could reveal atmospheric evolution patterns that reflect expansion effects through atmospheric loss and redistribution mechanisms operating during planetary expansion. Greenhouse gas concentration reconstruction reveals atmospheric composition evolution that could reflect changing atmospheric volume and atmospheric pressure through expansion-induced atmospheric modification. Greenhouse gas patterns potentially documenting expansion effects through atmospheric composition evolution that reflects changing atmospheric conditions during expansion episodes. Greenhouse gas analysis could provide atmospheric chemistry evidence for expansion through composition patterns that reflect atmospheric evolution. Atmospheric circulation pattern reconstruction reveals wind system evolution that could reflect changing planetary surface area. And atmospheric circulation modification through expansion-induced circulation pattern changes. Atmospheric circulation evolution potentially documenting expansion effects through circulation system evolution that reflects changing planetary surface characteristics during expansion episodes. Circulation pattern analysis could provide atmospheric dynamics evidence for expansion through circulation evolution that reflects planetary surface area changes. Precipitation pattern evolution and hydrological cycle reconstruction reveal water cycle characteristics that could reflect changing planetary surface area, and hydrological system modification through expansion-induced water cycle changes. Hydrological evolution potentially documenting expansion effects through water cycle evolution that reflects changing planetary surface characteristics during expansion episodes. Hydrological analysis could provide water cycle evidence for expansion through hydrological pattern evolution that reflects planetary expansion. Some believe atmospheric pressure evidence supports planetary expansion based on paleo-environmental reconstruction and atmospheric evolution analysis, while others suggest that atmospheric pressure variations reflect climate change and atmospheric evolution processes that operate without requiring planetary expansion, despite atmospheric pressure reconstruction techniques. The interpretation of atmospheric evidence for planetary expansion continues to be investigated as paleo-environmental reconstruction techniques improve and atmospheric evolution understanding advances. Atmospheric chemistry isotopic ratios preserve information about atmospheric evolution that could reflect expansion-induced atmospheric modification. Isotopic atmospheric analysis potentially documenting expansion through atmospheric chemistry evolution that reflects changing atmospheric conditions during expansion episodes. Isotopic analysis could provide atmospheric chemistry evidence for expansion through isotopic pattern evolution that reflects atmospheric modification during planetary expansion. Weather pattern evolution and storm system characteristics could reflect changing atmospheric dynamics associated with expansion-induced atmospheric circulation modification. Weather system evolution potentially documenting expansion effects through atmospheric dynamics, evolution that reflects changing planetary surface area during expansion episodes. Weather pattern analysis could provide atmospheric dynamics evidence for expansion through weather system evolution that reflects planetary surface area changes. The irony of atmospheric expansion evidence lies in its preservation of atmospheric condition information in geological records that could document planetary expansion while atmospheric processes that created these records operated under potentially different planetary conditions that remain difficult to distinguish from climate change effects. Atmospheric evidence potentially supporting expansion scenarios, while atmospheric interpretation remains complicated by climate evolution processes that could create similar atmospheric signatures without requiring planetary expansion. Atmospheric records preserving expansion signatures while atmospheric analysis faces challenges in distinguishing expansion effects from conventional climate change processes that create overlapping atmospheric evolution patterns. Lunar distance changes and tidal effects preserve information about Earth's gravitational field evolution and planetary size modifications throughout geological history. Lunar orbital evolution demonstrating systematic recession patterns that could reflect changing Earth gravitational binding and planetary radius evolution during geological time. Moon-Earth distance measurements reveal lunar recession rates of approximately 8 centimeters annually through laser-ranging precision measurements. Lunar orbital evolution potentially documenting Earth gravitational field changes that accompany planetary expansion through gravitational field modification effects on lunar orbital dynamics. Tidal friction mechanisms and tidal energy dissipation patterns create systematic lunar orbital evolution through gravitational interaction between Earth rotation and lunar orbital motion. Tidal effects causing Earth rotational deceleration while driving lunar orbital expansion through gravitational energy transfer. These tidal evolution processes could preserve signatures of Earth expansion through modified tidal dissipation rates and gravitational field changes that affect tidal interaction efficiency and lunar orbital evolution patterns during planetary expansion episodes. Ancient tidal rhythmite analysis in sedimentary formations preserves tidal cycle information that documents historical Earth-Moon distance relationships and tidal interaction characteristics. Rhythmite formations, recording tidal periodicity and tidal amplitude variations that reflect past gravitational interaction strength. Tidal rhythmite evidence potentially reveals Earth expansion through modified tidal characteristics that reflect changing planetary radius and gravitational field strength during rhythmite deposition periods. Earth rotation rate evolution demonstrates systematic rotational deceleration through geological time that reflects tidal friction effects and angular momentum conservation. Rotational evolution potentially preserving information about changing Earth moment of inertia that could reflect planetary expansion through modified mass distribution and planetary radius changes. Earth rotation history could document expansion through rotational dynamics that reflect changing planetary structure during expansion episodes. Gravitational field strength evolution affects tidal interaction efficiency and lunar orbital evolution rates. Gravitational field modifications during expansion potentially creating observable signatures in lunar orbital evolution and tidal dissipation patterns that reflect changing gravitational binding strength. Gravitational field evolution could provide gravitational evidence for expansion through modified gravitational interaction that affects tidal dynamics and lunar orbital characteristics. Coral growth band analysis in ancient coral formations preserves tidal cycle information and seasonal growth patterns that document historical tidal characteristics and Earth rotation periods. Coral paleontology potentially revealing expansion effects through tidal pattern evolution that reflects changing tidal interaction during coral growth periods. Coral growth evidence could provide biological documentation of expansion through tidal evolution that affects coral growth environments. Lunar formation theories and early Earth-Moon system evolution provide constraints on Earth expansion through lunar origin mechanisms and early gravitational interaction patterns. Lunar formation potentially establishing initial conditions for Earth-Moon system evolution that could be modified by subsequent planetary expansion. Lunar formation analysis could reveal expansion effects through early system evolution that reflects changing planetary conditions during lunar formation and early orbital evolution. Tidal heating effects on planetary structure demonstrate how tidal interaction creates internal heating and deformation that could contribute to planetary expansion through tidal energy input. Tidal heating potentially providing energy sources for expansion, while creating thermal expansion and structural modification that supports planetary growth mechanisms. Tidal heating analysis could reveal expansion energy sources through tidal interaction that contributes to planetary thermal and structural evolution. Paleontological tidal zone evidence preserves information about ancient tidal environments and tidal range characteristics that could reflect changing tidal interaction strength and Earth gravitational field evolution. Tidal zone fossil evidence potentially documenting expansion through tidal environment evolution that reflects changing tidal characteristics during fossil formation periods. Tidal zone paleontology could provide environmental evidence for expansion through tidal evolution that affects biological environments. Binary planet system comparisons reveal gravitational interaction patterns in other planetary systems that could provide analogues for Earth-Moon system evolution. Comparative planetology potentially establishing expansion signatures through gravitational interaction analysis that reveals expansion effects on planetary system evolution. Planetary system comparison could provide comparative evidence for expansion through gravitational interaction analysis. Satellite orbital evolution analysis for other Earth satellites, including artificial satellites, reveals gravitational field characteristics that could detect ongoing expansion effects. Satellite orbital analysis potentially providing contemporary evidence for expansion through orbital evolution that reflects changing gravitational field strength. Satellite tracking could provide observational evidence for expansion through orbital dynamics that reflect current gravitational field evolution. Some believe lunar orbital evolution provides evidence for Earth expansion based on gravitational field evolution analysis and tidal interaction modeling, while others suggest that lunar orbital evolution reflects conventional tidal friction and gravitational interaction that operates without requiring planetary expansion despite lunar evolution analysis techniques. The interpretation of lunar evolution evidence for planetary expansion continues to be investigated as lunar orbital modeling improves and gravitational interaction understanding advances. Tidal bore formation and tidal resonance effects could reflect changing tidal interaction strength associated with expansion-modified gravitational field and tidal dissipation characteristics. Tidal resonance potentially documenting expansion through tidal interaction evolution that reflects changing planetary conditions during expansion episodes. Tidal resonance analysis could provide tidal evidence for expansion through resonance pattern evolution that reflects planetary expansion. Earth-Moon barycenter evolution and gravitational center of mass evolution could reflect changing planetary mass distribution associated with expansion-induced mass redistribution and planetary structure modification. Barycenter evolution potentially documenting expansion through gravitational center evolution that reflects changing planetary characteristics during expansion episodes. Barycenter analysis could provide gravitational evidence for expansion through center of mass evolution that reflects planetary expansion. The irony of lunar expansion evidence lies in its utilization of moon orbital evolution to investigate Earth expansion, while lunar recession represents well-established astronomical phenomenon that operates through conventional tidal friction mechanisms. Lunar orbital evolution potentially preserving expansion signatures, while lunar recession demonstrates conventional gravitational interaction that appears independent of planetary expansion requirements. Lunar evidence creating potential expansion documentation, while lunar dynamics operate through established gravitational mechanisms that function without requiring planetary expansion, despite lunar evolution providing possible expansion signatures through gravitational interaction effects that could reflect planetary expansion influences on Earth-Moon system evolution. Seismic wave velocity changes throughout Earth's interior reveal temporal variations in deep Earth structure that could indicate ongoing planetary expansion or contraction through internal density modifications and seismic property evolution over time. Deep Earth seismic imaging through global seismic networks demonstrates mantle and core structure characteristics that could reflect expansion-induced internal architecture changes. Seismic tomography potentially detecting expansion signatures through systematic velocity changes and internal density evolution that accompanies planetary radius modification during expansion episodes. Seismic wave travel time analysis reveals internal Earth structure evolution through systematic monitoring of wave propagation characteristics. Travel time variations potentially documenting expansion effects through modified internal structure that affects seismic wave propagation through changing internal density and elastic property distributions. Travel time monitoring could provide seismic evidence for expansion through wave propagation analysis that reveals internal structure evolution during planetary expansion processes. Mantle convection pattern evolution affects seismic velocity structure through thermal and chemical convection that modifies internal density distribution. Convection evolution potentially reflecting expansion-induced internal circulation changes that create observable seismic signature modifications. Mantle convection analysis could reveal expansion effects through convection pattern evolution that reflects changing internal dynamics during planetary expansion through convection system modification. Core structure evolution and core mantle boundary characteristics could reflect expansion-induced internal architecture modification. Core structure potentially exhibiting expansion signatures through modified core geometry and core mantle interface evolution that accompanies planetary radius changes. Core structure analysis could provide deep Earth evidence for expansion through core evolution that reflects internal structure modification during planetary expansion episodes. Seismic anisotropy patterns reveal internal structure orientation and deformation characteristics that could reflect expansion-induced internal stress and strain patterns. Seismic anisotropy potentially documenting expansion through internal deformation signatures that reflect changing internal structure during expansion episodes. Anisotropy analysis could provide structural evidence for expansion through deformation pattern evolution that reflects internal stress modification during planetary expansion. Deep earthquake characteristics and earthquake mechanism evolution could reflect expansion-induced internal stress patterns and deformation processes. Deep earthquake analysis potentially revealing expansion signatures through earthquake mechanism evolution that reflects changing internal stress conditions during expansion episodes. Earthquake mechanism analysis could provide tectonic evidence for expansion through earthquake evolution that reflects internal stress modification during planetary expansion. Seismic discontinuity evolution and internal boundary characteristics could reflect expansion-induced internal structure modification. Seismic discontinuities potentially exhibiting expansion signatures through boundary evolution that reflects changing internal architecture during expansion episodes. Discontinuity analysis could provide internal boundary evidence for expansion through discontinuity evolution that reflects internal structure modification during planetary expansion. Inner core structure and inner core growth patterns could reflect expansion-induced core evolution. Inner core characteristics potentially revealing expansion signatures through core structure evolution that reflects changing core conditions during expansion episodes. Inner core analysis could provide core evidence for expansion through inner core evolution that reflects core structure modification during planetary expansion through core growth and core structure evolution. Seismic velocity gradients and internal property transitions could reflect expansion-induced internal structure evolution. Velocity gradient analysis, potentially documenting expansion through internal property evolution that reflects changing internal characteristics during expansion episodes. Velocity gradient analysis could provide internal property evidence for expansion through gradient evolution that reflects internal structure modification during planetary expansion. Free oscillation characteristics and planetary normal mode evolution could reflect expansion-induced planetary structure modification. Normal mode analysis potentially revealing expansion signatures through oscillation characteristic evolution that reflects changing planetary structure during expansion episodes. Normal mode analysis could provide planetary oscillation evidence for expansion through oscillation evolution that reflects planetary structure modification during expansion. Seismic wave attenuation patterns and internal energy dissipation characteristics could reflect expansion-induced internal structure modification. Attenuation analysis potentially documenting expansion through energy dissipation evolution that reflects changing internal characteristics during expansion episodes. Attenuation analysis could provide energy dissipation evidence for expansion through attenuation evolution that reflects internal structure modification during planetary expansion. Some believe seismic velocity evolution provides evidence for planetary expansion based on internal structure analysis and seismic monitoring techniques, while others suggest that seismic velocity variations reflect conventional internal evolution processes that operate without requiring planetary expansion despite seismic analysis capabilities. The interpretation of seismic evidence for planetary expansion continues to be investigated as seismic monitoring techniques improve and internal structure understanding advances. Crust-mantle boundary evolution and MOHO discontinuity characteristics could reflect expansion-induced crustal structure modification. MOHO evolution potentially revealing expansion signatures through crustal boundary evolution that reflects changing crustal structure during expansion episodes. MOHO analysis could provide crustal boundary evidence for expansion through boundary evolution that reflects crustal structure modification during planetary expansion. Regional seismic velocity variations and local structure evolution could reflect expansion-induced regional deformation. Regional seismic analysis potentially documenting expansion through local structure evolution that reflects changing regional characteristics during expansion episodes. Regional analysis could provide local evidence for expansion through regional structure evolution that reflects local deformation during planetary expansion. The irony of seismic expansion detection lies in its utilization of seismic waves that propagate through potentially expanding planetary interior to investigate expansion processes that could modify wave propagation characteristics. Seismic monitoring potentially detecting expansion through wave propagation changes, while seismic waves provide measurement tools that could be affected by expansion processes they attempt to measure. Seismic velocity evolution potentially documenting expansion, while seismic measurement techniques rely on wave propagation through internal structure that could be modified by expansion processes, creating measurement challenges where expansion detection methods could be influenced by expansion processes that affect measurement reliability through internal structure modification that influences seismic wave propagation characteristics used for expansion detection. Satellite altimetry and GPS monitoring achieve unprecedented precision for detecting planetary surface changes through continuous space-based measurement systems that monitor Earth's shape, size, and gravitational field with millimeter accuracy across global scales. Advanced satellite geodesy utilizes laser ranging, radar altimetry, and GPS positioning to create comprehensive planetary monitoring networks capable of detecting subtle surface elevation changes, gravitational field variations, and planetary radius modifications that could indicate ongoing expansion or contraction processes operating over decadal to century timescales. Global Positioning System Constellation provides continuous three-dimensional position monitoring for thousands of ground stations worldwide. GPS networks achieving centimeter-level precision for detecting surface motion and planetary deformation, while establishing reference frames that could reveal systematic planetary expansion through coordinated baseline length increases. GPS measurement precision approaches theoretical requirements for expansion detection over multi-decade observation periods, positioning accuracy potentially achieving sensitivity sufficient for detecting expansion rates predicted by geological expansion theories. Satellite laser ranging networks utilize ground-based laser systems to measure distances to retroreflector-equipped satellites with millimeter precision, SLR providing independent validation of GPS measurements while establishing highly accurate distance measurements between ground stations and orbital satellites that could detect planetary radius changes through systematic distance modifications. Laser ranging achieves ultimate precision for satellite distance measurement while providing redundant measurement capabilities for expansion detection through multiple independent measurement techniques. Very long baseline interferometry employs radio telescope networks to measure intercontinental distances with sub-millimeter precision through astronomical radio source observations. VLBI achieving extraordinary accuracy for detecting planetary size changes through baseline expansion measurements that could reveal expansion at rates below GPS detection thresholds. Interferometric measurement precision approaches physical limits for distance measurement while providing ultra-high accuracy validation for expansion detection through independent measurement techniques. GRACE satellite gravity missions monitor gravitational field variations that could reflect planetary mass redistribution or planetary size changes through precision gravity mapping. Gravitational field measurements potentially revealing expansion signatures through systematic gravitational field modifications associated with planetary growth. Gravity monitoring provides geophysical evidence for expansion through gravitational field evolution that could accompany planetary radius increase through expansion-induced gravitational field modification. Radar altimetry from satellite platforms measures surface elevation changes with centimeter precision across oceanic and continental regions. Altimetry providing comprehensive surface monitoring that could detect expansion through systematic elevation increases associated with planetary radius growth. Surface elevation monitoring potentially reveals expansion effects through elevation pattern evolution that reflects planetary surface modification during expansion episodes. Satellite orbit determination and orbital evolution analysis provide sensitive tests for gravitational field changes that could accompany planetary expansion. Orbital mechanics potentially revealing expansion signatures through systematic orbital evolution that reflects modified gravitational field strength during expansion episodes. Orbital analysis could provide gravitational evidence for expansion through orbital evolution that reflects gravitational field modification during planetary expansion. International Terrestrial Reference Frame Establishment creates global coordinate systems that provide frameworks for detecting planetary deformation and expansion through coordinated measurement campaigns. Reference frame maintenance potentially revealing expansion through systematic coordinate evolution that reflects changing planetary geometry during expansion episodes. Reference frame analysis could provide geodetic evidence for expansion through coordinate system evolution that reflects planetary geometry modification. Tide gauge networks monitor sea level variations that could reflect planetary expansion through changing oceanic basin volumes. Sea level measurements potentially providing indirect evidence for expansion through oceanic volume changes associated with planetary radius increase during expansion episodes. Sea level monitoring could provide oceanic evidence for expansion through sea level evolution that reflects oceanic basin modification during planetary expansion. INSAR interferometric analysis utilizes satellite radar interferometry to detect surface deformation with millimeter precision. Interferometric measurements potentially revealing expansion signatures through surface deformation patterns that reflect planetary expansion processes operating over satellite observation periods. Interferometric analysis could provide surface deformation evidence for expansion through deformation pattern evolution that reflects planetary expansion. Precision orbit determination for multiple satellite systems provides comprehensive monitoring of orbital evolution that could detect gravitational field changes associated with expansion. Multi-satellite analysis, potentially revealing expansion signatures through coordinated orbital evolution that reflects systematic gravitational field modification during expansion episodes. Multi-satellite analysis could provide comprehensive evidence for expansion through orbital evolution coordination that reflects planetary expansion. Some believe satellite monitoring systems provide adequate precision for detecting planetary expansion based on measurement capability analysis and expansion rate predictions, while others suggest that expansion detection requires measurement precision beyond current capabilities despite remarkable satellite measurement accuracy. The adequacy of current satellite precision for expansion detection continues to be evaluated as satellite technology advances and expansion theories are refined. Next-generation satellite systems, including improved GPS constellations and advanced gravity monitoring missions, could achieve enhanced sensitivity for detecting subtle planetary expansion. Future satellite capabilities potentially providing definitive expansion detection through improved measurement precision and extended observation baselines. Future satellite development could establish expansion detection capabilities through technological advancement and measurement precision improvement. Data analysis techniques, including statistical analysis and signal processing methods, provide frameworks for extracting expansion signatures from satellite measurement data. Data analysis potentially revealing expansion signals that remain below individual measurement precision through statistical analysis of measurement time series and coordinate evolution patterns. Statistical analysis could provide expansion detection through data processing that reveals expansion signals through measurement pattern analysis. The irony of satellite expansion monitoring lies in its achievement of extraordinary measurement precision that approaches sensitivity required for expansion detection, while potential expansion operates at rates that require measurement precision sustained over time in periods that exceed satellite mission durations. Satellite technology achieving millimeter precision for planetary measurements, while expansion detection requires sustained precision over decades to centuries that challenge technological system longevity and measurement program continuity. Satellite monitoring providing ultimate measurement capability, while expansion detection demands measurement persistence that transcends individual satellite mission lifetimes and technological development cycles. Alternative physics and modified gravity theories propose exotic mechanisms that could drive planetary expansion through fundamental physics modifications that transcend conventional geological and gravitational processes. Theoretical physics investigations exploring variable physical constants, extra-dimensional effects, and modified gravitational field equations that could create planetary expansion through mechanisms beyond standard geological expansion models. These alternative physics scenarios suggest that planetary expansion could result from fundamental physics evolution rather than conventional thermal expansion, mass accumulation, or phase transition processes. Variable physical constant theories, including scalar tensor gravity and cosmological models, predict temporal evolution of fundamental constants, including gravitational constant, fine structure constant, and particle masses that could affect planetary structure and gravitational binding over geological timescales. Fundamental constant variation could drive planetary expansion through weakened gravitational binding when gravitational constant decreases, modified atomic physics when fine structure constant evolves, or altered nuclear physics when particle mass ratios change over cosmic time. Extra-dimensional physics scenarios propose that planetary expansion could result from extra-dimensional effects, including dimensional compactification changes, brane-world dynamics, and higher dimensional gravitational leakage that affects four-dimensional gravitational physics. Extra-dimensional models suggest that planetary radius could increase through dimensional geometry evolution, higher dimensional gravitational modifications, or extra-dimensional energy input that drives planetary growth through mechanisms inaccessible to conventional four-dimensional physics analysis. Modified gravity theories, including FR gravity, scalar tensor theories, and non-local gravity, propose gravitational field equation modifications that could create planetary expansion through altered gravitational physics that transcends general relativity limitations. Modified gravity could drive expansion through gravitational anti-screening effects, scalar field evolution, or non-local gravitational corrections that reduce gravitational binding and permit planetary radius increase through modified gravitational dynamics. Quantum gravity effects on macroscopic scales could create planetary expansion through quantum gravitational corrections to classical gravitational physics. Quantum gravity potentially affecting planetary structure through space-time quantization, gravitational field quantization, or quantum gravitational phase transitions that modify planetary gravitational binding. Quantum gravitational effects could accumulate over geological time to create measurable planetary expansion through quantum corrections to classical planetary physics. Dark energy interactions with planetary matter could drive expansion through exotic energy components that create repulsive gravitational effects. Dark energy potentially affecting planetary structure through modified stress energy tensor contributions that create anti-gravitational effects within planetary interiors. Dark energy interactions could provide energy sources for planetary expansion, while creating exotic matter effects that transcend conventional matter physics through dark energy coupling to ordinary matter. Vacuum energy effects and Casimir force modifications could affect planetary structure through quantum vacuum interactions with planetary matter. Vacuum energy potentially creating expansion forces through modified vacuum pressure and quantum field fluctuation effects that affect planetary equilibrium radius. Vacuum energy interactions could provide quantum mechanical expansion mechanisms through vacuum pressure modification that affects planetary hydrostatic equilibrium. Cosmological expansion coupling to planetary scales could create planetary expansion through cosmic expansion effects that influence planetary physics. Cosmic expansion potentially affecting planetary structure through modified cosmic background gravitational fields, or cosmic expansion stress effects that propagate to planetary scales. Cosmological coupling could drive planetary expansion through cosmic evolution effects that transcend local planetary physics through cosmic scale influences on planetary structure. Torsion gravity and gauge theory. Gravity approaches propose gravitational field modifications through additional gravitational degrees of freedom, including space-time torsion and gauge field contributions that could affect planetary gravitational binding. Torsion gravity could create planetary expansion through modified gravitational field equations that include torsion contributions to planetary gravitational physics through gauge theoretical gravitational modifications. String theory effects on planetary scales could create expansion through stringy gravitational corrections, extra-dimensional string dynamics, or string theoretical modifications to gravitational physics that affect planetary structure. String theory could drive planetary expansion through fundamental string interactions that modify gravitational binding, extra-dimensional string effects that influence four-dimensional planetary physics, or string theoretical corrections to general relativity that affect planetary equilibrium. Emergent gravity scenarios propose that gravitational phenomena emerge from more fundamental quantum information processing or thermodynamic processes that could evolve over time to create planetary expansion through modified emergent gravitational effects. Emergent gravity could drive expansion through evolution of underlying information processing systems or thermodynamic conditions that generate gravitational phenomena through emergent mechanisms that could change over geological time. Some believe alternative physics provides plausible mechanisms for planetary expansion based on theoretical physics developments and fundamental physics evolution possibilities, while others suggest that alternative physics scenarios remain speculative despite theoretical frameworks for exotic expansion mechanisms that transcend conventional geological processes. The viability of alternative physics expansion mechanisms continues to be investigated as theoretical physics advances and fundamental physics understanding develops. Unified field theory attempts to combine gravitational, electromagnetic, weak nuclear, and strong nuclear forces could predict planetary expansion through unified field evolution or fundamental force coupling modifications that affect planetary physics. Unified theories could drive expansion through fundamental force evolution that modifies gravitational binding or unified field effects that create expansion forces through fundamental physics unification. Loop quantum gravity effects on planetary scales could create expansion through discrete space-time structure effects that modify gravitational physics at macroscopic scales. Loop quantum gravity potentially affecting planetary structure through space-time quantization effects that accumulate to create planetary expansion. Loop quantum gravity could drive expansion through discrete gravitational effects that modify classical gravitational binding through quantum gravitational space-time structure. The irony of alternative physics expansion mechanisms lies in their proposal of exotic expansion processes that transcend conventional physics while requiring extraordinary theoretical physics that remains beyond experimental verification. Alternative physics providing expansion explanations through mechanisms that exceed current experimental access, while conventional geological expansion mechanisms operate through established physics that could be experimentally investigated. Exotic physics creating expansion possibilities through theoretical frameworks that transcend empirical verification, while conventional expansion mechanisms utilize established physics that remains accessible to experimental investigation despite expansion detection challenges. Biological adaptation to changing gravity explores whether evolutionary biology and physiological adaptations preserve signatures of varying gravitational field strength associated with planetary expansion over geological time. Evolutionary evidence potentially documenting gravitational field evolution through biological responses to changing gravitational environments during species evolution. Biological systems demonstrate remarkable sensitivity to gravitational variations, while evolutionary adaptation could preserve information about historical gravitational conditions through physiological characteristics and evolutionary adaptations that reflect gravitational field evolution during biological evolution. Gravitational biology research reveals organism responses to modified gravitational environments, including altered growth patterns, physiological stress responses, and developmental modifications that could reflect evolutionary adaptation to changing gravitational conditions. Laboratory gravitational experiments demonstrate significant biological effects from gravitational modifications, while suggesting that biological systems could adapt to gradual gravitational changes associated with planetary expansion through evolutionary selection for gravitational tolerance and physiological adjustment mechanisms. Skeletal structure evolution in vertebrates reveals bone density and structural characteristics that could reflect adaptation to changing gravitational loading during evolutionary history. Skeletal evolution potentially documenting gravitational field changes through bone architecture that reflects gravitational stress environments during vertebrate evolution. Vertebrate skeletal systems demonstrate gravitational sensitivity, while evolutionary skeletal modification could preserve information about gravitational environments during species evolution through structural adaptation. Cardiovascular system evolution and circulatory adaptations could reflect physiological responses to changing gravitational field strength during evolutionary development. Cardiovascular evolution potentially documenting gravitational changes through circulatory system characteristics that reflect gravitational environments during cardiovascular system evolution. Circulatory systems demonstrate gravitational dependence, while evolutionary cardiovascular modification could reveal gravitational field evolution through physiological adaptation to gravitational environments. Plant growth responses to gravitational variations demonstrate gravitotropism and structural adaptations that could preserve information about gravitational environments during plant evolution. Plant evolution potentially documenting gravitational field changes through growth patterns and structural characteristics that reflect gravitational conditions during plant evolutionary development. Plant gravitational responses demonstrate sensitivity to gravitational variations, while evolutionary plant adaptation could preserve gravitational field information through structural evolutionary modifications. Muscle development and locomotion system evolution could reflect adaptation to changing gravitational loading conditions during evolutionary history. Muscular system evolution potentially documenting gravitational changes through locomotion, adaptations, and muscle architecture that reflects gravitational environments during muscular system evolution. Muscular systems demonstrate gravitational dependence, while evolutionary locomotion modification could reveal gravitational field evolution through physiological adaptation to gravitational loading conditions. Inner ear evolution and balance system adaptations could preserve information about gravitational field variations during evolutionary development. Vestibular system evolution potentially documenting gravitational changes through balance system characteristics that reflect gravitational environments during vestibular system evolution. Balance systems demonstrate gravitational sensitivity, while evolutionary vestibular modification could preserve gravitational field information through physiological adaptation to gravitational sensing requirements. Biomechanical stress analysis of ancient organisms reveals structural characteristics that could reflect gravitational loading conditions during fossil organism lifetimes. Paleontological biomechanics potentially documenting gravitational field evolution through fossil structural analysis that reveals gravitational stress environments during ancient organism development. Fossil structural analysis could provide paleontological evidence for gravitational field changes through biomechanical stress reconstruction. Metabolic rate evolution and energy expenditure adaptations could reflect physiological responses to changing gravitational work requirements during evolutionary development. Metabolic evolution potentially documenting gravitational changes through energy expenditure patterns that reflect gravitational work environments during metabolic system evolution. Metabolic systems demonstrate gravitational dependence, while evolutionary metabolic modification could reveal gravitational field evolution through energy expenditure adaptation. Size limitations and scaling relationships in biological systems could reflect gravitational constraints on organism size during evolutionary development. Biological scaling potentially documenting gravitational field changes through size limitation evolution that reflects gravitational constraint environments during organism size evolution. Biological scaling demonstrates gravitational limitations, while evolutionary size modification could preserve gravitational field information through scaling relationship adaptation. Flight evolution and aerial locomotion adaptations could preserve information about gravitational field strength during flying organism evolution. Flight system evolution potentially documenting gravitational changes through aerial locomotion, characteristics that reflect gravitational environments during flight system development. Flight systems demonstrate gravitational sensitivity, while evolutionary flight modification could reveal gravitational field evolution through aerial Locomotion adaptation. Some believe biological adaptations preserve evidence for changing gravitational conditions based on evolutionary biology analysis and gravitational biology research, while others suggest that biological characteristics reflect conventional evolutionary pressures that operate without requiring gravitational field changes, despite biological gravitational sensitivity. The interpretation of biological evidence for gravitational field evolution continues to be investigated as evolutionary biology understanding advances and gravitational biology research develops. Reproductive system evolution and developmental adaptations could reflect physiological responses to changing gravitational environments during evolutionary development. Reproductive evolution potentially documenting gravitational changes through developmental characteristics that reflect gravitational environments during reproductive system evolution. Reproductive systems demonstrate gravitational dependence, while evolutionary reproductive modification could preserve gravitational field information through developmental adaptation. Sensory system evolution and perception adaptations could preserve information about environmental conditions, including gravitational field characteristics during sensory system evolutionary development. Sensory evolution potentially documenting gravitational changes through perception system characteristics that reflect gravitational environments during sensory system evolution. Sensory systems could preserve environmental information, while evolutionary sensory modification could reveal gravitational field evolution through perceptual adaptation. The irony of biological gravitational adaptation lies in its potential preservation of gravitational field evolution information through biological characteristics that could document changing gravitational conditions, while biological adaptation operates over time scales that transcend individual organism lifespans. Evolutionary adaptation potentially documenting gravitational field changes through biological characteristics, while adaptation processes require multiple generations to preserve gravitational field information through evolutionary modification. Biological systems demonstrating gravitational sensitivity, while gravitational field evolution occurs over geological timescales that exceed direct biological observation, despite biological adaptation potentially preserving gravitational evolution signatures through evolutionary characteristics that reflect changing gravitational environments over evolutionary time. Technological detection methods and future monitoring systems could achieve a sensitivity required for detecting slow geological expansion rates through advanced measurement technologies including space-based interferometry, quantum sensors, and next-generation satellite systems that surpass current measurement precision limitations. Future monitoring capabilities potentially provide definitive expansion detection through technological advancement that achieves measurement sensitivity sufficient for detecting expansion rates predicted by geological expansion theories. Advanced technology creating expansion detection possibilities through measurement, precision improvement, and extended observation baselines. Space-based interferometry utilizing orbital interferometer arrays could achieve extraordinary precision for detecting planetary expansion through baseline measurements between spacecraft positioned at planetary distances. Space interferometry potentially providing ultimate sensitivity for expansion detection through measurement techniques that transcend atmospheric limitations and terrestrial measurement constraints. Orbital interferometer systems could establish measurement precision approaching theoretical limits, while providing stable measurement platforms for detecting subtle planetary expansion over extended observation periods. Quantum sensor technology including atomic interferometry, quantum gravimeters, and quantum accelerometers could achieve unprecedented sensitivity for detecting gravitational field variations and planetary motion characteristics associated with expansion. Quantum sensing, potentially providing revolutionary measurement capabilities for expansion detection through quantum mechanical measurement precision that transcends classical measurement limitations. Quantum sensor networks could establish quantum measurement precision for expansion detection through quantum mechanical sensing advantages. Next-generation global positioning system enhancements, including improved satellite constellations, enhanced signal processing, and augmented measurement precision could achieve expansion detection sensitivity through GPS technology advancement. Future GPS capabilities potentially providing expansion detection through positioning precision improvement that achieves measurement sensitivity sufficient for detecting geological expansion rates. Advanced GPS systems could establish positioning precision requirements for expansion detection through satellite technology improvement. Laser ranging networks utilizing advanced laser systems and improved retroreflector technology could achieve enhanced precision for satellite distance measurements that could detect planetary expansion through systematic distance modifications. Advanced laser ranging potentially providing expansion detection through distance measurement precision that exceeds current laser ranging capabilities. Enhanced laser ranging could establish distance measurement precision for expansion detection through laser technology advancement. Gravitational wave detection technology adaptation for planetary monitoring could achieve sensitivity for detecting gravitational field variations associated with planetary expansion. Gravitational wave detector modifications potentially providing expansion detection through gravitational field monitoring that utilizes gravitational wave detection precision for planetary gravitational field analysis. Gravitational wave technology could provide gravitational field monitoring for expansion detection through detector technology adaptation. Atomic clock networks utilizing optical atomic clocks and quantum clock technology could achieve timing precision sufficient for detecting fundamental physics variations associated with expansion, including gravitational redshift modifications and fundamental constant changes. Atomic timing potentially providing expansion detection through precision physics measurements that reveal expansion effects on fundamental physics. Atomic clock networks could establish timing precision for expansion detection through atomic clock technology advancement. Distributed sensor networks, including global monitoring arrays and coordinated measurement campaigns, could achieve statistical precision for expansion detection through measurement redundancy and statistical analysis that transcends individual measurement precision limitations. Distributed monitoring potentially providing expansion detection through statistical measurement techniques that reveal expansion signals through coordinated measurement analysis. Distributed networks could establish statistical precision for expansion detection through measurement coordination. Machine learning applications to expansion detection could identify subtle expansion signatures in measurement data through artificial intelligence pattern recognition that transcends conventional statistical analysis capabilities. Machine learning potentially providing expansion detection through automated pattern recognition that identifies expansion signals in measurement time series and coordinate evolution patterns. Artificial intelligence could enhance expansion detection through pattern recognition that reveals expansion signatures in measurement data. Quantum communication networks for measurement coordination could achieve instantaneous measurement synchronization across global distances for coordinated expansion monitoring. Quantum communication potentially providing expansion detection enhancement through measurement coordination that transcends classical communication limitations for distributed measurement campaigns. Quantum communication could improve expansion detection through measurement coordination enhancement via quantum communication technology. Cryogenic technology applications to measurement precision could achieve enhanced sensitivity for expansion detection through ultra-low temperature measurement conditions that reduce thermal noise and improve measurement stability. Cryogenic measurement potentially providing expansion detection through measurement precision enhancement that utilizes cryogenic temperature advantages for measurement noise reduction. Cryogenic systems could establish measurement precision for expansion detection through temperature control technology. Some believe future technology developments will achieve the sensitivity required for definitive expansion detection based on technological advancement projections and measurement precision improvement trends. While others suggest that expansion detection may remain beyond technological capabilities despite anticipated technology advancement and measurement precision improvement, the prospects for technological expansion detection continue to be evaluated as measurement technology advances and detection requirement analysis improves. Satellite constellation coordination for expansion monitoring could achieve enhanced measurement coverage and precision through coordinated satellite measurements that provide comprehensive expansion monitoring across global scales. Satellite coordination potentially providing expansion detection through measurement coverage enhancement that utilizes multiple satellite systems for comprehensive expansion monitoring. Coordinated satellites could establish comprehensive expansion monitoring through satellite system coordination. International collaboration for expansion monitoring could achieve sustained measurement campaigns over extended periods through coordinated international measurement programs that transcend individual institutional capabilities. International cooperation potentially providing expansion detection through sustained monitoring that maintains measurement precision over extended observation periods required for expansion detection. International collaboration could establish sustained expansion monitoring through cooperative measurement programs. The irony of technological expansion detection lies in its potential achievement of measurement precision sufficient for detecting expansion through technological advancement. While expansion detection requires measurement persistence over timescales that exceed technological development cycles, future technology potentially achieving expansion detection sensitivity, while expansion detection demands measurement, program continuity that transcends technological system lifetimes and institutional stability periods, technological advancement approaching expansion detection requirements, while expansion detection requires sustained measurement precision over periods that challenge technological system longevity and measurement program maintenance capabilities that exceed individual technological development and institutional sustainability timescales. Planetary science and astronomy applications of Earth expansion research connect terrestrial expansion investigations to planetary formation theory and exoplanet studies. Expansion research revealing universal processes that affect planetary evolution across astronomical timescales, while providing comparative frameworks for understanding planetary development throughout solar system and exoplanetary systems. Earth expansion studies establish theoretical foundations for planetary expansion mechanisms that could operate universally. Planetary expansion representing fundamental planetary evolution process that transcends individual planetary systems through universal expansion mechanisms operating across astronomical environments. Exoplanet characterization benefits from Earth expansion research through expansion detection techniques and expansion mechanism understanding that could identify expansion signatures in exoplanetary systems. Exoplanet studies potentially revealing expansion processes operating in other planetary systems through transit photometry, radial velocity measurements, and direct imaging observations that could detect planetary radius evolution. Exoplanetary expansion detection could provide comparative evidence for expansion universality, while establishing expansion as fundamental planetary evolution process. Solar system planetary expansion investigations utilize Earth expansion research methods for detecting expansion in other solar system bodies including Mars, Venus, and outer planet moons. Comparative planetary expansion studies potentially revealing expansion universality through expansion detection across multiple planetary bodies within solar system. Solar system expansion research could establish expansion as solar system-wide phenomenon while providing multiple planetary laboratories for expansion investigation through comparative planetary analysis. Planetary formation theory integration with expansion mechanisms explores how planetary expansion processes operate during planetary formation and early planetary evolution. Planetary formation potentially incorporating expansion processes that continue throughout planetary evolution rather than representing post-formation modification processes. Planetary formation research could reveal expansion as fundamental planetary development mechanism that operates from planetary formation through continued planetary evolution. Comparative planetology applications to expansion research utilize multiplanetary expansion studies for understanding expansion universality and expansion mechanism variations across different planetary environments. Comparative studies potentially revealing expansion principles that transcend individual planetary characteristics while establishing universal expansion laws. Comparative planetology could establish expansion universality through multiplanetary expansion investigation across diverse planetary systems. Asteroid and small body expansion studies investigate whether expansion processes operate in smaller planetary bodies including asteroids, comets, and planetary satellites. Small body expansion, potentially revealing expansion mechanisms that operate across planetary size ranges while establishing expansion as universal planetary process. Small body research could extend expansion investigation to smaller planetary objects while revealing expansion mechanisms across planetary size spectra. Planetary magnetic field evolution through expansion processes could affect magnetic field generation and magnetic field characteristics during planetary expansion. Magnetic field evolution potentially documenting expansion effects through magnetic field strength and magnetic field structure modifications associated with planetary expansion. Magnetic field studies could provide planetary evidence for expansion through magnetic field evolution analysis during planetary expansion episodes. Planetary atmospheric evolution during expansion could affect atmospheric pressure, atmospheric composition, and atmospheric dynamics through expansion-induced atmospheric redistribution over changing planetary surface area. Atmospheric evolution potentially documenting expansion effects through atmospheric characteristic modification during planetary expansion. Atmospheric studies could provide planetary evidence for expansion through atmospheric evolution analysis during planetary expansion. Tidal heating effects on planetary expansion investigate whether tidal interaction between planetary bodies creates expansion through tidal energy input and tidal heating that drives thermal expansion and structural modification. Tidal heating potentially providing expansion energy sources while creating expansion mechanisms through gravitational interaction between planetary systems. Tidal studies could reveal expansion energy sources through tidal interaction analysis between planetary bodies. Impact cratering effects on planetary expansion explore whether impact events affect planetary expansion through impact energy input and impact-induced planetary modification. Impact cratering, potentially influencing expansion through impact heating and impact structural modification that affects planetary expansion processes. Impact studies could reveal expansion influences through impact event analysis on planetary expansion mechanisms. Planetary geology applications to expansion research utilize geological investigation techniques for detecting expansion signatures in other planetary bodies through planetary surface analysis and planetary structure investigation. Planetary geology potentially revealing expansion evidence through geological formation analysis and geological structure evolution on other planetary bodies. Geological studies could provide planetary evidence for expansion through geological investigation across multiple planetary systems. Some believe Earth expansion research provides fundamental insights for planetary science based on expansion mechanism, universality, and planetary evolution principles, while others suggest that Earth expansion research remains specific to Earth conditions despite comparative planetology applications and universal expansion mechanism possibilities. The universality of expansion mechanisms continues to be investigated as planetary science advances and expansion research develops across multiple planetary systems. Planetary interior structure evolution during expansion could affect seismic properties and internal structure characteristics. Planetary interior evolution potentially documenting expansion effects through internal structure modification during planetary expansion episodes. Interior studies could provide planetary evidence for expansion through interior structure evolution analysis during planetary expansion across multiple planetary bodies. Planetary climate evolution during expansion could affect climate patterns and climate system characteristics through expansion-induced climate modification. Climate evolution potentially documenting expansion effects through climate pattern evolution during planetary expansion episodes. Climate studies could provide planetary evidence for expansion through climate evolution analysis during planetary expansion across different planetary environments. The irony of planetary expansion universality lies in its potential operation as fundamental planetary evolution process, while remaining undetected in individual planetary systems including Earth. Expansion potentially representing universal planetary development mechanism while operating below detection thresholds for individual planetary observation. Planetary expansion possibly affecting all planetary systems while expansion detection remains challenging for individual planetary monitoring despite expansion representing fundamental planetary evolution process that operates across astronomical timescales and astronomical environments. Universal expansion processes potentially creating planetary evolution while remaining invisible to planetary observation through expansion rates that transcend individual planetary system observation capabilities despite expansion, potentially affecting planetary development across astronomical systems. The imperceptible nature of geological change demonstrates how slow geological processes operate below human perception thresholds, while creating dramatic planetary transformation over geological timescales. Earth expansion representing ultimate example of imperceptible change, where potential planetary growth proceeds at rates that remain invisible to human observation, despite potentially creating profound planetary modification over millions of years. These imperceptible geological processes reveal fundamental limitations in human temporal perception, while highlighting how geological systems operate according to timescales that transcend human experiential frameworks. Geological change proceeding continuously yet invisibly through mechanisms that exceed human perceptual capabilities. Human temporal perception limitations constrain geological process observation to timescales approaching human lifespans, while geological processes operate over timescales spanning millions to billions of years. Temporal perception boundaries creating observational challenges for detecting geological change that operates continuously over periods that exceed human generational experience. Human perception evolved for detecting immediate environmental changes, while geological processes operate through temporal frameworks that transcend individual human experience and historical human observation periods. Geological rate calculations reveal process speeds that often measure millimeters per year or centimeters per millennium. Geological change rates falling below direct human detection thresholds, while accumulating over geological time to create dramatic planetary modification through imperceptible incremental change. Mountain formation, continental drift, and potential planetary expansion operate at rates that remain invisible to direct human observation, while creating substantial planetary transformation through accumulated geological change over extended time periods. Measurement technology development approaches sensitivity required for detecting imperceptible geological processes through precision measurement techniques that achieve accuracy sufficient for detecting subtle geological change over human observation timescales. Technological advancement potentially enabling detection of geological processes that remain naturally imperceptible to human observation. Measurement precision improvement creates technological capability for detecting imperceptible change while revealing geological processes that operate below natural human perception thresholds. Historical geological observation reveals dramatic planetary changes documented through geological records, while geological change remains imperceptible during human-centered observation periods. Geological evidence demonstrating substantial planetary transformation over geological time, while geological change processes remain invisible during individual human lifetimes. Geological records preserve evidence for dramatic change, while geological change operates imperceptibly during human temporal experience. Comparative geological analysis across different timescales reveals how geological change magnitude correlates with observation duration. Extended observation periods revealing substantial geological change, while short observation periods suggest geological stability despite continuous geological process operation. Timescale effects demonstrate how observation duration affects geological change. Detection, while revealing temporal perspective, influences on geological process understanding. Technological analogy comparisons illustrate imperceptible change through technological examples including computer processing speeds and electronic system evolution that operate below direct human perception while creating substantial technological transformation over extended periods. Technological change providing analogies for geological imperceptible change through technological process rates that exceed human perception capabilities. Technological examples demonstrate imperceptible change universality across multiple systems that operate below human perception thresholds. Statistical analysis requirements for detecting imperceptible change demand. extended observation periods, and measurement precision that exceeds natural human capabilities. Statistical detection of imperceptible change, requiring technological assistance and extended measurement campaigns that transcend individual human observation capabilities. Statistical methods provide frameworks for detecting imperceptible change, while revealing measurement requirements that exceed natural human detection capabilities. Environmental change detection challenges demonstrate how gradual environmental modification remains imperceptible during individual human experience, while creating substantial environmental transformation over extended periods. Environmental change, providing examples of imperceptible change that affects human systems while remaining below direct human detection during environmental change progression. Environmental examples illustrate imperceptible change effects that influence human experience while remaining invisible during change progression. Biological evolution examples demonstrate imperceptible change through evolutionary processes that operate below human observation timescales, while creating dramatic biological transformation over evolutionary time periods. Evolutionary change, providing biological examples of imperceptible change that create substantial biological modification through accumulated evolutionary change over extended periods. Evolutionary examples illustrate imperceptible biological change that creates dramatic biological transformation through accumulated change over evolutionary timescales. Cosmological change examples demonstrate imperceptible change through astronomical processes including stellar evolution, galactic rotation, and cosmic expansion that operate below human perception thresholds while creating substantial astronomical transformation over cosmic timescales. Cosmological change, providing astronomical examples of imperceptible change operating across cosmic systems. Astronomical examples illustrate imperceptible change universality across cosmic systems that operate below human temporal perception capabilities. Some believe imperceptible geological change represents fundamental characteristic of geological systems based on geological process analysis and temporal scale investigation, while others suggest that geological change remains detectable through appropriate measurement techniques despite imperceptible change during direct human observation. The imperceptible nature of geological change continues to be investigated as measurement technology advances and temporal scale understanding improves. Perception psychology research reveals human temporal perception limitations and cognitive frameworks that constrain geological change detection. Psychological investigation potentially explaining why geological change remains imperceptible through cognitive limitations that affect geological process observation and geological change recognition. Psychological studies could provide cognitive frameworks for understanding imperceptible change detection limitations through human perception analysis. Education applications for imperceptible change utilize geological examples for illustrating temporal scale concepts and change detection challenges. Educational frameworks potentially improving geological understanding through imperceptible change. Examples that demonstrate geological process characteristics and measurement challenges. Educational approaches could enhance geological understanding through imperceptible change illustration and temporal scale education. The ultimate irony of imperceptible geological expansion lies in its potential for creating dramatic planetary transformation through processes that remain completely invisible to direct human observation. Planetary expansion potentially proceeding continuously throughout human history while remaining below human detection thresholds, despite potentially creating profound planetary modification that affects all human experience. Imperceptible expansion demonstrating ultimate geological change paradox, where fundamental planetary processes operate beyond human perceptual access, while potentially determining planetary characteristics that define human environmental experience. Geological imperceptibility creating observational challenges where planetary processes that could define planetary evolution remain invisible to planetary inhabitants despite continuous operation throughout human civilization and human scientific investigation. Imperceptible change representing fundamental limitation in human understanding of planetary systems that operate according to temporal and spatial scales that transcend human experiential frameworks despite human dependence on planetary systems for human existence and human civilization development. The question floats through geological time like a whisper carried across millions of years. Whether our planet grows imperceptibly beneath our feet while we measure continents to millimeter precision yet remain blind to changes that unfold over timescales that dwarf human civilization. In this contemplation of planetary patience, every mountain becomes a moment of Earth's slow breathing, every ocean basin a pause between geological heartbeats that echo across eons while we live entire lifetimes in the space between two ticks of the planetary clock. Perhaps the ground swells beneath our cities at rates so gentle that generations pass without noticing the subtle expansion. Cosmic dust settling grain by grain while radioactive decay warms the planetary interior and phase transitions occur in pressures beyond imagination. The Earth dreams in geological time. Continental positions shifting like thoughts in a sleeping mind, while magnetic reversals flip the planetary memory and tidal forces massage the planetary body through gravitational embraces with celestial companions. Every measurement becomes an attempt to catch the planet in motion. GPS satellites orbiting overhead like mechanical angels recording coordinates that might shift by millimeters across decades of observation. Scientists peer into seismic waves traveling through planetary depths, searching for velocity changes that could reveal expanding interior architecture, while the planet keeps its deepest secrets locked in pressures and temperatures that exist nowhere else in human experience. The expanding Earth hypothesis whispers of continental puzzle pieces that fit too perfectly on smaller spheres. Pangea reconstructions suggesting our ancestors walked on a more intimate planet where oceanic basins had yet to stretch between familiar lands. In this vision, the Atlantic Ocean represents not ancient spreading but recent planetary growth. Oceanic crust marking expansion episodes while magnetic stripes record the timing of planetary breathing that operates beyond human temporal comprehension. Yet the measurements remain stubbornly silent about dramatic change. Precision instruments detecting crustal motion with extraordinary accuracy while potential expansion proceeds at rates that would require centuries of observation to confirm or deny. We live in the gap between measurement precision and geological process rates. Technological capability approaching but not quite achieving the sensitivity required to catch the planet in the act of growing. The irony deepens as we realize that the very processes that might drive expansion operate through mechanisms we can barely observe directly. Cosmic bombardment adding mass grain by grain, thermal expansion occurring deep within the planetary interior, gravitational constants potentially evolving at rates that accumulate over geological time to create measurable effects. The planet may be performing the ultimate magic trick, changing dramatically while appearing completely stable to observers whose lifespans represent mere instants in geological time. In this planetary meditation, consciousness confronts the limits of perception and the challenge of understanding systems that operate on scales vastly exceeding human experience. We become detectives investigating a crime that may be occurring too slowly to observe, gathering evidence for processes that unfold over timescales that make human civilization appear as a brief flicker in the planetary narrative. The search continues in precision laboratories and satellite networks, in deep drilling projects and computational models that attempt to bridge the gap between human observation capabilities and geological process rates. Whether the Earth expands beneath our feet or maintains stable dimensions, the investigation reveals the profound challenge of understanding planetary systems that operate according to their own temporal logic, indifferent to human curiosity yet fundamental to human existence. In this contemplation of imperceptible change, every breath synchronizes with the possibility that our planet breathes too, so slowly that entire human civilizations rise and fall between inhale and exhale. The expanding Earth remains a geological koan, teaching us about the limits of perception while revealing the extraordinary patience required to understand planetary processes that unfold across the vast scales of geological time. Perhaps the deepest truth lies not in whether the Earth expands, but in the recognition that planets operate according to temporal and spatial scales that humble human understanding. Geological processes proceeding with majestic indifference to human observation, while potentially creating the very foundation upon which human civilization depends for its existence. Planetary change occurring at rates that transcend human perception while remaining fundamental to planetary evolution and planetary habitability